Okay, so
Open it here and
Laura. Oh, okay.
yep.
And
And also make sure your speakers are muted as well. It could
It's
create some
muted?
feedback.
Okay.
It's just make sure everything else is muted except for this computer
Got
here.
it. Okay.
Um,
Okay, so I'm actually talking there.
No, you're talking through this mic,
my God,
this one,
okay.
or this one. You can choose any
Okay,
of them.
okay.
This one here right now, you could just speak where you are right now.
Okay.
It doesn't feel like it's very powerful, but it's going through all the speakers right there. And as you can tell, it's going through the Zoom. You could hear us pretty well. So you don't really have to lean into it. You can just stay where you
Talk
are.
normal. Okay.
If you want to use another microphone, you could always, they're all already connected to the system. So you just open it and you could use this one as well.
So I still cannot share screen.
You
by
could
the way.
use this one as well. It's your choice
Okay.
as you prefer. But it's just easier to just stand there and use this one.
Oh.
Yep.
No. It says no.
You don't have permission? Make it screen.
Okay, now I can. This works. Okay. Okay, so how late? At 1? But that's okay. People can grab food and start.
So just a couple of things. If you lose the image on the screen at some point, it's just like this connector is a bit, this computer is a bit loose there. So just make sure you don't really touch
Touch
it.
it, okay.
That's weird, but also another tiny detail. If there's people on Zoom that you're going to present on Zoom, you're going to talk.
Okay.
If this sound is too loud or not loud enough, you just want to you want to adjust the volume of the computer actually. So just see.
FM, okay.
And just like because the volume of the people in Zoom are coming from this computer, which is plugged to the system. And if you want to lower down their volume and not lower down your voice in the room, so independently.
Okay, so I have to ask them if they would.
No, you could just simply just do it here. So if it's too loud, just lower the volume here. If it's not loud enough, just bring it up. And this is just going to affect the volume of the people in Zoom in the room here.
Okay.
But it's not going to affect your microphone and everything because you don't want that. So that's pretty much it.
Okay.
That's all you need to know. Quick test here just to make sure. Okay, got it. Perfect. So you're all set.
Okay. Well, if you have any problem, I'll just email you. You will be around.
Or you could, you're on Slack.
Yeah, I'm
Like,
Slack.
send
Yeah,
a message
okay.
on Slack.
Okay.
It's my name and my email address.
Okay, thank you.
So yeah, if there's any issue, message me. I'll be there real quick. Okay, just so when you're done.
they're muted now. And if it's not obvious, we will be here. Yeah, it's a piece of art. It's all in. Most pleasant. You're going to be so happy today that you phone in and give the best deal on this order.
Hey, everyone.
Hello. Can you hear me as well, I guess, Xavier?
Yeah, I can hear you well. Can you hear me, guys?
Yeah, fantastic. See how this
Well,
works for the most part. Oh. We're just trying to figure out the
I think it's up and lower, maybe.
Do you mind talking a bit more, Xavier? Just adjusting the volume here.
Oh, it's Gav here. I guess if you are talking to me, can you hear me well?
No, is that better? I think for the no more yelling. Okay. Yeah, sorry. So maybe I'll at least you want to, I'll start stuff for like 30 seconds and introduce the person who I don't think I've talked to either of you about. So that'll be a start. So no, this is Xavier. He's presenting today. So like the overall idea for this workshop is, Mila actually has like a lot of people working for the IDT department. There's also roughly 6 or 7 different reinforcement learning groups at Mila. We don't always communicate with each other the best. So maybe we can at least eliminate some of we all create the exact same software and we can collaborate a little bit better. But a lot of the idea at the end is to maybe even give like a short list of things that we can ask Mila and the IDT team to help build for us to make the research easier. So that's why it's great to see what everyone's using basically in the lab, and then they'll know what you're using and they can maybe even support that and like do bug fixes for those types of things too. So then today, so to sort of start out, yeah, Xavier here is from, I think a company or an organization called AIM, which does a lot of like experiment tracking, things like that. But I'll let you to please, Xavier, please take it off and tell us more about what you do and kind of about the process. Thank you.
Thanks. Thanks, everyone. A little bit of correction. I believe Xavier is from IDT. My name is Jeff.
Oh,
all good though. All good though. No worries. Yeah. Thanks for inviting me. I'm really excited to share a little bit of our work. So this is potentially going to be kind of a higher level overview over experiment tracking. Actually, can I share my screen?
Yeah, it should work properly.
Yeah, just a second there. So we prepared the hopefully real quick presentation around essentially a high level overview of in general, experiment tracking. What is experiment tracking? I will share a little bit about AIM, basically what we do at AIM/AIM stack, and a little bit of our views of essentially where the landscape is going to go, etc. And yeah, so I named my talk. Now that this was a little bit about the systems, the famous book, The Structure Interpretation of Computer Programs. I've named my talk with an homage to the book, The Structure Interpretation of Experiment Trackers. So yeah, as I mentioned, we are going to talk about the high level, what is experiment tracking, why you need it, what does AI metadata have to do with it. We'll talk about AIM, it's what we are building, our team, what we are focused on, and kind of why we are working on it. A little bit about the experiment tracking landscape. Then we will touch upon the future of AI dev tools, kind of our view of it, and if time permits, I'll try to share a funny RL and the early days of AIM story. Yeah, so essentially, the question is, why do we need to track the training runs at all, right? So if we look at what are the training runs by itself, they are essentially the experiments kind of are not cheap because they run on GPUs, and GPUs are usually, depending on what cluster you use, that is it on AWS, is it on Azure or other systems, they're usually not so cheap, and so these are quite expensive, operations, and so not only that, but also when we are building models, they're really hard to debug and comprehend, and so the models are usually sets of numbers, and so they're not like code that you can read and understand what's going on. And usually when we are trying to build models, we end up running a bunch of different training runs, and so the number of runs tend to grow in numbers, and also a lot of the times it's really easy to waste expensive GPUs. So for instance, when run has stalled or something has happened to your run, practically it could be the GPU would be running, but nothing would be learning. Or like a subset of that would be when model training kind of slows down, like for instance, the loss plateaus or some metric, just doesn't stops like progressing the way like the researcher would expect it to. And also another reason that we tend to track the training runs is the runs are usually have this multidimensional basically nature, and what does it mean, right? So the training runs are multidimensional. There's a lot of moving pieces when you're doing machine learning training. So there, for instance, the code it changes all the time. The data you could be playing, for instance, with different pre-processing steps. Training environment, this one doesn't change too often, but when it changes, for instance, the GPU driver versions could easily change. Maybe some update on a cluster that the IT team has done, and then voila, then some things changed, and needs to be restarted, and maybe it's hard to reproduce. So model architecture, obviously, then hyperparameter tuning. Sorry, there, yeah. So hyperparameter tuning, which means lots of different run get started, where different combinations of specific set of hyperparameters are being tried. So in this environment, as a result, we end up having thousands of runs, training runs, where each run could have hundreds of metrics, and each run could have also hundreds of hyperparameters. So these are fairly like high dimension of things that could change while you're trying to build a model, essentially. And so how to keep track of these changes across these dimensions? So usually what we have seen people are tracking when they're training models, it's kind of in a few categories. And so usually we have seen people, researchers tend to track a lot of the system related stuff. especially when you're training large models, say like a transformer type, that's training on multi-GPU environment, especially if it has, I don't know, 100-something GPUs. So you want to be able to have a decent idea of how each of your node is doing, how each of your GPU is doing, how each of the node is doing, where the GPU is actually, installed, etc. You also want to keep track of your data sets. So you want to be able to connect the different version of your data or different pre-processing to basically the different system that basically connect all the dots, including samples and different annotations that you're trying out. Maybe in the beginning you're just trying on a smaller data set. So just to get a feel of the code before you actually set the proper training running. So you just want to keep track of everything. And obviously the code where you may end up changing the model architecture, and you would end up running hyperparameter tuning, which would then generate, as I mentioned, lots of runs. And this doesn't include images, text, audio, and other meta. So the above stuff could be like run-through metrics, and then a lot of intermediate values come into play. So you want to, you're like training a generative adversarial network. You may want to track lots of intermediate images, lots of text, or other types of problems. And so these are just kind of an overview of dimensions you are going to end up researchers deal with when they're trying to train models. So what are the core expectations from experiment trackers? So you want your experiment tracker to compare your training runs. You want it to help you with reproducibility, and you want it to help you with the management of your runs. And let's go through each of them and see what do they mean. So comparing training runs is one of the fundamental activities during the research. Essentially, one of the things you're always trying to do as a researcher is to try and find the patterns in the past and present training runs, which means literally the comparison, so that you can make the decision on the next steps, or maybe go back to the other pre-processing step, or maybe just play with maybe compare across the seeds, or maybe oh, this works, okay, let's run with different seeds to see if with different seeds that we would obtain the same result. So therefore, it's just the comparison of different runs is such a core activity for the researcher that the experiment tracking tool needs to be able to actually help you accomplish that goal. The faster, the better, and especially with the many dimensions that I mentioned across the number of runs, etc. You want the UI to be kind of nice and fast as well. So so experiment trackers should be good at comparing lots of experiments. And reproducibility. So basically, you want to be able to run the past training workflow on the same data set to try to get the same result. Basically, to achieve this, we usually recommend, and we have seen many researchers do, the full state. Basically, you need to try to do your best to capture the full state of your kind of training, which includes the code, the environment, the data version, the seed values. Seed values are pretty neat one, because we have seen this, like some really detail-oriented researchers tend to really spend attention on this, because when you capture the seed values, then it just doesn't allow you to kind of get into sometimes into the delusion that your model is doing well, because then you can play with the seed and then really make sure that it works well. So and then the governance training, which means you want to be able to usually when you end up having large number of multi-dimensional runs, you want to be able to be on top of the runs, understand how things have started, how access them, right? You want to be able to kind of group them in kind of the related ones together. So for instance, usually when like one like experiment starts to work, then you end up, trying to go deeper and like changes more granular, hyperparameters of different, moving pieces to then nail in with your model, right? So those tends to be related, but there is all sorts of ways the relatedness could be defined. Access, essentially you want to always have access to your runs and whatever has been tracked with it. So it's not, I mean, you can always have, maybe if you track with the terminal or some custom code, yeah, you can access it from terminal, but then you also sometimes want to access with decent UI or something more structured. Obviously create delete runs and the runs lineage, because for instance, if you're training large models on a large cluster, the more GPUs you're training simultaneously on, the more tendency these systems get to actually break. And so sometimes there is a pretty deep run lineage. So for instance, TR11 that we have been like translating, playing with lately, it's kind of like a one run, but it has many different runs that are one created from each other with a small tweak, but then they're kind of connected with each other. So there's like a pretty long runs lineage, and usually created by some technical issues that comes with the GPUs and setup like SLAR, etc. Yeah, so essentially what I've been talking about the experiment tracking, and the reason we have put the experiment tracker into double quote is that we believe that experiment tracker doesn't do justice to what actually these tools are. We believe them more like the AI metadata tools, right? And then examples of AI metadata would be basically either your metrics, your hyperparameters, intermediate images, text, voice. You could track Plotly visualizations. You could track all sorts of other objects, whatever you need for your experiment to like understand, to debug them, etc. So we consider that all of it as metadata, including the environment related, the cluster, etc. And so this brings us to AIM. So essentially, we're a group of 12 engineers. We have been working on this open source project for about 2.5 years now. We have started from like really early days. At this stage, we have built a system that is really good at tracking a ton of machine learning experiments. We are one of the, I think we are alongside with TensorFlow, we're integrated with Metaseq. So yeah, so we have quite a bit of progress here. So I'll share a little bit about what is AIM and then kind of switch to a little bit of our vision and the landscape. So, so essentially AIM is an AI metadata tracking and comparison library. It has a powerful UI, which has several different sections. The most prominent one and the paradigm we are building and pushing forward is called Explorer, which allows to compare a lot of experiments in like really short period of time, like in a few clicks. There's ways to bookmark. There's a lot of different states of these explorers, and you can obviously access their run details. But a lot of the tool right now is evolving around the explorers, which are quite powerful. They allow to compare images, scatter plots, hyperparameters, metrics, and soon Plotly figures as well. So yeah, and basically it allows to create thousands of multidimensional training runs, basically manage thousands of runs, and just visualize a lot of different types of machine learning metadata. So it's fully open source. It's Apache 2 license. It's community driven. We are really tightly working with the community. Basically no feedback kind of, we try to not miss any feedback and really proactive about it. And we believe we are building the foundations of an ecosystem. I'll share a little bit about that later in the talk. So what are the main components? So AIM has 3 main components. It has a AIM SDK. It's a Python library essentially that allows you to track and query machine learning metadata, basically quite a dense granularity. You can save like lots of steps, lots of sequences, And it's really full of integrations with a lot of the essential ML tools like NumPy, Pandas, and we are going to integrate with Orion and PyTorch Lightning. Basically, most of the tools you use is already integrated. So, and AIM storage, which is a quite scalable storage that's capable of storing lots of multidimensional runs. It's modular, means runs are kind of isolated, but it allows to get a lot of deep functionalities of comparison, easy copy, move, delete runs, and they're extendable, which means you can not only store metrics, images, but you can store basically any Python object. And then UI, which is a metadata management and visualization tool that sits on top of the AIM storage. And it allows deep comparison exploration of multidimensional metadata. So basically what AIM
wasn't like at Agora, like I didn't see people like,
sorry,
the SystemsRL workshop, like it was supposed to be like this event is in person at Agora at Mila, but I didn't find. Do you know that?
sorry guys.
Like it's still
Someone just
going
had
on.
their-
If you like look on the Zoom.
Oh, there is other side of there are two entrances.
Ah,
Someone have their mic on?
and one more thing, like this I received, like what is this? Not sure.
Sorry.
Because I didn't find anyone's name which I know. So like, is it a mistake or something?
I think they make already.
Excuse me, Rahul, can you hear
Because
me?
no one I know is.
Yeah,
Rahul?
Yeah.
they would have water completed like what they gave and then
Oh yeah.
they would have.
Hmm.
I thought
Okay.
Rahul was asking a question.
Because I didn't know like what is happening. So I'm like,
Yes. But Jackie's groups come. They are having status calls.
I'm sorry, I'm not
Hey.
in it. Okay. That's okay.
You can go.
Hello.
All right. Very sorry for that, but I think everyone except for Gev is muted now and this room. Please
No
proceed
worries at all.
for the
Yeah.
technical difficulty.
Yeah, I hope this is not a very kind of tedious technical one. We try to make this as more like a workshop style where we can go a little bit kind of relatively technical, but not too much, to give some idea of like what it takes to build an experiment tracking and like some of the inner works of it. But yeah, it's kind of a couple of slides only. Yeah, I'm kind of also a little bit late. So yeah, basically what AIM SDK does, it has kind of 3 building blocks. It allows to store object, which is basically image, metric, audio, distribution, primitives, all sorts of things. And then you end up tracking them as sequence, which is, a series of homogeneous objects, kind of metric becomes like, for instance, sequence of floating, numbers, images, right? And then a container, which is a set of interconnected sequences, which in a machine learning terms is the training run. It's the kind of unit you're trying to actually, there's all this connected, metric set of images, etc. They're all like as a container. So that's an abstraction we use underneath. And basically, AIM SDK allows to do a lot of manipulations with the tracked metadata. So it has a Pythonic interface to define and track metadata, through code. You can basically write like a Python statements against everything you have tracked as part of your training run. And then it has a lot of built-in adapters with popular ML frameworks. And for instance, there is a screenshot here. That's how a typical query could look like if you're using the AIM SDK. So AIM storage essentially is kind of foundational part. It's built on top of RocksDB. It's quite scalable. It can take lots of runs, thousands of runs. It's very modular, which means 2 runs kind of don't know about each other, but kind of they can be moved, deleted, etc. And you can write lots of parallel, runs at the same time, which is usually like we have folks using with Slarm and lots of other similar tools. So, and you can store not only existing objects, you can define a new object and basically store any type of Python object and sequences of them. So, okay. And then UI, it's just a bunch of different explorers that are basically tools that enable a deep exploration analysis of the tracked objects. So you can search them, you can group them, sort them, manipulate them. For instance, you can, like, in terms of metrics, you can change the x-axis into another metric, basically all the regular training tracking stuff. And obviously, there is a runs management that allows to group and understand, just organize the runs. So this is how the AIM UI looks like. If you know, for instance, this is the metrics explorer, and this is how the images explorer looks like. And we are building a bunch of these explorers right now. So as I mentioned, the figures explorer is coming out, which is going to help compare thousands of plot leaks if you want to track something custom. Yeah, so our point of view. So we believe that AI metadata. We believe that AI metadata. Oh, sorry. We believe that AI metadata is a key asset in the AI infrastructure. It's generated across the whole AI pipeline, but kind of end up collected by different tools. You have evaluation tools. You have, you know, production monitoring tools, etc. So we believe that AI metadata is the glue of the infrastructure. It connects different parts of the pipeline together. And one version of that is basically the one generated during experiments, and so which is also famously known as experiment tracking, which is kind of this talk is about. So yeah, but essentially we believe that one metadata tool and many applications and seamless integrations is the way to go. So for instance, active monitoring, if you're like training on several good number of GPUs, sometimes your training stalls, you want to get like you want to get notifications about your training, but what if you want to get deep notification, you know, the notifications that has quite a sophisticated, for instance, condition over metric values, etc. That, you know, you can write actual functions on top of your metrics that can, you know, specifically notify you in, you know, very specific cases. Usually handy when you're training large models. I would presume this would be also relevant for reinforcement learning. So for instance, automatic benchmarking. A lot of the benchmarking is basically taking a data set and running a model through it, and, you know, just organizing the results, etc. These are all metadata activities, and so this could be also heavily automated if need be. It's kind of these are all, we consider them as metadata applications. And custom objects, you can, for instance, what if you want to track images with specific, you know, rectangles on top of them, for instance, the segmentation, you know, type, you know, use cases and compare those images instead of the, you know, regular. So you should be able to not just rely on matplotlib, but you know, actually pass on Python objects and compare all sorts of things together in the UI, and also deep integrations with your favorite tools, like or Orion and others. So while we are working on it, basically our mission is to democratize the AI developer tools. We are building an ecosystem that enables free open source AI infrastructure for everyone. And the core aim, you know, is always open source and non-crippleware. And we believe that a lot of the external AI applications are like plugins, are like, you know, basically metadata applications that needs to be built, like one really well built metadata kind of tool. And so basically we believe that you own your metadata and build with it or around it, and build reusable and seamlessly integrated you know, plugins. So this is why we are working, because we don't see a tool out there that just enables everybody to kind of build off of each other work in terms of when it comes to you know, AI metadata. So existing solutions, a little bit about the landscape. There's like, we have grossly simplified, divided things into open source and closed source. the most famous one is obviously TensorBoard, the OG. TensorBoard is easy to get started. It's not great for comparison and sometimes for training management, arguably. The MLflow is good for some kinds of experiments. Say that's kind of less image heavy or less metric heavy, right? But MLflow is also sort of a platform. For instance, say it's not just experiment tracking. It's actually a small part of it. You can do all sorts of cool things with MLflow, like a whole pipeline can be managed with MLflow. Model registry. It has so many components. So I guess putting the MLflow in experiment tracking category is a little bit of this, not so much justice, but nevertheless. So AIM is kind of the new kid in the block. We are absolutely focused on metadata, trying to build the best metadata tool out there that just collects a ton of it and allows you to compare very in depth, and obviously weights and biases, is probably one of the most famous out there. There is a few other like enterprise-driven ones, FOMAT-ML and Neptune AI. So this is what the landscape looks like these days when it comes to experiment tracking. So basically, what do we think is the future of AI dev tools? And I'm like 1 minute late, but almost done. AI dev tools and experiment tracking is, we believe that the open source AI developer tool ecosystem is the future, where basically down the line, for instance, weights and biases is a platform that's based off of a non-open source kind of situation. But we believe that the future of AI infrastructure is going to be fully open source, very similar to what exists right now for the regular software, I guess, software 1.0, where you see the dominant, building blocks is Kubernetes, React, which are kind of built very similar to, in a way that, you can build around them. If you, for instance, you're using Kubernetes, you can attach Nginx, you can attach load balancer, a bunch of different things to it. And similar to React, there's like a vast component system that you don't need to build things from scratch when you're starting with it. And so we believe the similar type of movement is going to happen with the AI infrastructure. And we believe we are trying to, also push with our work towards that. And so, so metadata tracking, we believe that there's going to be a stack of, so metadata doesn't get only generated at the training level, it gets generated at all sorts of levels at the machine learning infrastructure, data pre-processing, obviously the experiments, evaluation, production monitoring. These are all sequences of different objects like numbers or images, right? And so these different visualizations are like a type of visualization you can actually render for just that collected metadata. So we believe that there is going to be a stack of open source tools that are going to be deeply integrated with each other. Say there is going to be, for instance, metadata tools that's going to help with visualization, comparison, monitoring of basically pipelines. There are going to be compute engines like, for instance, PL, Slarm, a bunch of others are coming out. And pipeline tools like Metaflow, organizing different parts of the pipeline together. So again, Kubernetes and React are an example of that. So I'm done with my presentation. I'm about I guess about more than 5 minutes up. So I'm happy to answer questions if there are some. How does AIM user experience differ from other experiment tracking frameworks like weights and biases?
Yeah, so we've got a little bit of time. Mostly because I think everyone wants to grab food really quick, and then and there are a couple of questions online. Okay, I don't know. All right. So maybe we can fit in parallel. So I'm going to give you 1 or 2 questions online, I guess, Gev, and then if people could start grabbing the food while it's still hot with the usual kind of rules, if I think there's enough like slices for everyone, and then come back for more after everyone's got food.
Sure. So should I wait for to answer the questions before folks grab the food, or should I just go ahead with it?
Oh, you can go ahead now. Yes, please.
Oh, yeah, okay. So the first question is from Charlie. Is there an RL specific logging in your tool? For example, eval and training speed aggregation, or robot joint position tracking using URDF files. Well, there is a way to fix the seed there in AIM. So there, I had this funny story that I wanted to tell about the RL. So we had launched AIM in 2020, October of 2020. Essentially, we had built this tool for our friend who was participating in the WMT20 competition, basically, at the time, two of us. So we launched it on Reddit, and one of the early users was Jay Kyun Kim. So he's a guy from Seoul National University. So it seems to be he's very famous in some of the RL circles because a lot of his later publications have been on ICLR, NeurIPS, etc. And so one of our largest realizations when we actually had the first chat with him was that he was tracking a ton of metrics, like thousands of experiments per week, hundreds of metrics per experiment, etc. So that conversation has been very impactful for us, where we ended up really optimizing the storage and the rest of the backend so that it can withhold that level of scale. So yeah, so in terms of RL specific, if I go back to the question again. Well, AIM is a metadata library. So you can use to track all sorts of stuff with it. You can also track eval. You can also track train. You can go even beyond with it. So yeah, there is a support for seed aggregation. There is support for all sorts of aggregation, I guess, because that's what we are really focused on. That allows to aggregate metrics across different parameters that should pass to us. I'm not sure about the robot joint position tracking URDF files. Yeah, that sounds like a custom object which could be added easily down the line, because as you can track literally anything you want, like HTML files, etc. So how does AIM? Does that make sense? If there be follow up, or I can move on.
Okay, I think. Yeah, you can probably follow up a bit, like feel free to chat about more of the questions, sort of like in the chat that's available to the meeting. But yeah, in order just to stay on time, it'd be great. And we could maybe thank our speaker again, and we can move on to the next speaker. So thank you very much, especially for doing this last day. We really appreciate it. All right. And then the next speaker, if you're ready. You can go ahead and share your screen. That's you. How's it going, Max?
Good. I am. Let's see if this works. Can you guys see my screen?
Yeah, looks great for us.
All right, perfect. Perfect. I think I have a hard stop at 2 p.m. your time, so I'll force you guys to be on schedule. Yeah, so just to get started, my talk is on JAX, and specifically JAX from the perspective of switching to JAX as someone who's worked in PyTorch for a long time, which I think is pretty common at Mila. That was certainly my situation. So JAX has a lot of advantages. PyTorch, so first off, everybody loves PyTorch, right? It's readable, it's simple, everything's intuitive. The only problem with PyTorch is its support for really fancy stuff isn't great. So this really hit me when I was trying to implement some more complicated meta-RL algorithms, for example. Most people at Mila don't really use TensorFlow, but it's pretty fast, it's kind of readable, it's got okay for support for stuff. JAX, though, is I think where the action really is right now. It's not as readable as PyTorch, but it can be incredibly fast, and you can do pretty much anything in it. If you want to do second order optimization, very straightforward. You want to do metagradient at RL, very straightforward. You want to, literally compile your replay buffer to C++, you can totally do that too. And so JAX can let you really optimize RL code. So for me, as someone who was like the #1 compute user at Mila for 2 years in a row, this was a really big deal. So right now, you're probably, if in the audience for this talk, you're probably using PyTorch because most of Mila historically has used PyTorch. And what I really want to convince you is that you should be using JAX. So what actually is JAX at the end of the day? Basically, you take a version of NumPy and you write a lot of architecture on top of it to let it compile down to C++. Then you port that compiled code to GPU or TPU. You add support for native parallelization. And then on top of that, Alphabet now uses JAX really, really heavily for all of its reinforcement learning work. So they're really good libraries for reinforcement learning. I'll cover the little bit of those at the end of the talk, but you may have heard of Dopamine and Acme, which have lots of implementations for stuff. And there's a library, very good library for reinforcement learning primitives called RELAX or RLAX that basically can let you to implement whatever reasonably straightforward thing you want to do in like 2 lines of code. So why is it that people aren't already all using JAX? Well, okay. So first off, JAX basically contains a copy of NumPy that lets you do PyTorch style tracing. So if you do jax.jit on a function, the first time you compile that, you call that function, it'll actually compile down to much faster code. So like here's something I wrote yesterday, just a simple stupid matrix power thing. And if I run this the hard way, it's going to be very, very slow. But if I call jax.jit on it, it magically gets about 10 times faster. And so you can see here I'm using JNP, which is just the JAX internal copy of NumPy that has all of the extra tracing. So the reason people aren't all using JAX though is it's pretty unintuitive in a lot of cases. So any JAX function has to be pure, which means you essentially can't have any side effects. So if you're familiar with functional programming, Haskell, for example, SML, this will be pretty familiar to you. But if you're not, the key idea is that anything your function does, especially including your neural network's train function, has to pass through your Python function's return statement. Nothing else is allowed. And so you cannot do PyTorch style optimization and I'll go into some examples of what this actually means you can't do later on. The other annoying thing about JAX is there's limited execution flow. So in PyTorch, I can have whatever chain of like if, for, while statements I want, and it just works, right? JAX is not like that. If I have a dynamically evaluated if statement, while loop, anything like that, it just won't work. So there are ways around this. You essentially can compile a lot of different versions of your function for every different control flow you might have, or you have to use a TensorFlow style, much more formalized control flow set of code. And we'll look at that in a little bit. So the bad thing about that is it's a pain to write. The good news is once you've written it, it's really, really fast. And then the third and last bit that I think gets people is RNG states in JAX have to be manually handled. So you are creating and passing around RNG objects throughout your JAX code. If you don't do this, you'll end up getting the same random number over and over again. Stuff just won't work. Any JAX implementation you start with, though, will do this roughly the right way. So it's not hard to figure out what to do. And the good news is that once you do this, JAX code is easy to make pretty much 100% deterministic, which is nice. So let's look at some code that probably would look pretty familiar to a PyTorch user, but that doesn't actually work. So we create a model and an optimizer. Maybe this is like the first line of your training code, essentially. We write a train step that takes a loss function, or takes some inputs and some outputs, calls the model on the inputs, computes like a squared loss.
Can you hear us, Max?
Yeah.
I've got a quick question for you.
Sorry, Max, I just thought I'd ask if you can go back to the previous slide, please. And you might be talking about it right now, actually.
Sure.
You're talking about how fast things get when you JIT them, right? So I've had several times working with JAX that something will take like forever to JIT, like on the order of 10 minutes or half an hour. And then it's going to be not that noticeably faster than what I'd already written. Do you have a sense of what might be going on there?
Yeah, it really depends on what the function is. First of all, I'm going to go into one common failure case a little later on, but you have to be really, really sure that it's not actually rejitting the code every time you call it, because it is very easy to do that. The other situation you may run into is where if you're only calling one unitary JAX operation, like a single mapmul or something like that, it's the amount of overhead you're paying is not actually, for like basic Python operations, is not actually that large. So where JIT really shines is when you're doing a lot of stuff all at once. So for example, for me, JITting a training function will usually cut the time the train step takes by, oh, I don't know, probably a comfortable order of magnitude at least. But again, one matmul, you won't see much. So the reason this this matrix power gets so much better if you JIT it is because we're doing the matmul over and over again, and you're actually mostly paying for the Python for loop in this. If you JIT it, the for loop goes away. It becomes just like some C++ code that does something 100 times in a row really quickly. And as a result of that, it just speeds up dramatically.
Cool.
Does that? Okay, cool.
Yeah, that helps.
Yeah,
And
and feel free to jump in with other questions.
Just a quick follow-up to that matmul. Is it doing something better than just unrolling the loop?
This matmul just unrolls the loop, but you could write an alternative matmul that would not unroll the loop. That would like actually use XLA, the library it compiles to. And I've got an example of that down here. So this is what a while loop looks like in JAX. So you have a condition, you have a loop body, and you just call this special while loop function that applies the loop body every time the condition is true.
Thank you.
So it's annoying to write this sort of code, but it does speed things up a lot. Yeah, so just going back to this. So this is an example of what doesn't work in JAX. So you create this model and optimizer outside of your train step, and then you try to update the model in the train step. You have side effects, like this train step is doing something that's not purely reducible to its inputs and its returns. And so JAX will either fail to compile this, or if it does somehow magically compile this, it won't actually work. It won't update your parameters. So this is how JAX code needs to get written. And it's a little bit unintuitive, I think, coming from PyTorch. But once you're used to it, it's not that bad. So your train step will take like a model class, a model definition, which is static because the model definition controls your execution flow. What basically, as I said before, JAX can't do dynamic control flow. So every time you pass in a new kind of model, it's going to recompile the function for the different like fixed control flow induced by that model. Same thing for the optimizer. So those are quote unquote static. And then things like parameters, the optimizer state, your inputs, your outputs, those are just normal. It doesn't have to recompile for different values of those. Then you take the loss function, you compute the gradients, you get your updates, you apply the updates, and then you just directly return the new parameters and the new optimizer state. So as you can see, we've gotten rid of those side effects. So this function is now pure in the functional programming sense, and it will actually do what you want. So this is an example of a loop body, of a loop that doesn't work. We're doing this if jnp.sum grads is less than 1 break. So we're trying to implement like a Python while loop here. And this won't work because it's trying to do dynamic control flow. But if you do this fancy JAX lax while loop with a condition, a body, and so on, it does actually work. So just moving on. Yeah, so the actual workflow if you're in JAX is basically start off without JIT, without the compilation, and just write some code that works. And it's basically at that level equivalent to writing NumPy. Then progressively add JIT, start compiling your code from the innermost functions, like simple things that you're sure are correct and don't have side effects, until you get to the point where you can JIT the entire training loop. Once you've done that, you're about 90% of the way there. The only fancy other things you can do in JAX, besides for JITting things outside of the main body of your training, are to do parallelization, FP16, that sort of thing. By the way, I can't see the chat, so if there are questions, people should just say them. And feel free to jump in. So one core detail of JAX is vectorization. So you can take a function. So Python has this function called map, which identically applies one function to every element of a container, like a list or a tuple, that sort of thing. And JAX can do the same thing. So if I give you a function and then use this function called vmap, I can make it operate across like a batch dimension, for example, uniformly. And if you do this, you can both make your code much more readable and improve your compilation times by a lot. Because now all you have to do is to compile this simple inner function and then tell JAX, apply the inner function over and over again. And if you don't actually, if you just try to use native Python for loops, your code can be much slower. No, so vmap is cool. It's, like I said, it's basically just the Python map function. But where things really get nice in JAX is that there's a version of vmap called pmap that just directly applies a function on a separate compute device for every element of the tuple. So this lets you basically arbitrarily parallelize your programs. So I can just say, like, I have a batch size of 8. I want to run each of those elements on a different device, a different GPU. And if you have 8 GPUs, it'll just work. So how you actually use this? You annotate your function with jax.pmap. You tell it what the static arguments are. It's the same as before. And then you just call the function. So the only fancy thing you have to do if you're running JAX in parallel is to use this function, this extra step called pmean, which syncs the gradients between your various devices. If you don't do that, essentially you're keeping 8 copies or however many copies of the parameters you have around, 1 for each device. And if you don't sync the gradients, they'll eventually diverge. That's all. So, there we go. So what this actually looks like in practice, you have to replicate out your parameters to each device. Then you have to distribute your data across the devices. That's this reshape here. So we're essentially creating 8 smaller mini batches, or local device count smaller mini batches, 1 for each device. You pass it to the train step, and that's it. It just works. So in my experience, this is much, much easier than trying to do PyTorch data parallel, and especially distributed data parallel, which had something like a 20% failure rate on Mila cluster or Compute Canada in the past. This really just works out of the box. It works, including outside of Google. It just works on Mila cluster and Compute Canada too, which is really, really nice. Like, this lets you do larger scale training without having to do a lot of extra infrastructure work for it. So development tips for JAX, because you'll need this. It is a little bit of a pain to work with. So PDB and IPDB work. You can still inspect your shapes and so on. Any operations that don't take gradients and aren't JITted should always use basic NumPy. The jax.numpy has a lot of extra tracing in it, which will make your code much slower. If you can get away with it, so remember how in JIT we have to specify what is static, what has to be recompiled. Always use this format if you can, static arg names, rather than specifying the number. It's just much better style, and you'll save yourself a lot of really confusing bugs. Only make arguments static if you know that they have to be static, because so essentially only make an argument static when you have confirmed that the control flow depends on the value of that argument. If you flag an argument as static when it's not, say like you're passing in the training step index and you call that static, you're going to recompile your code every single time you try to run your function, which will really make your code very, very slow, insufferably slow. So JIT should always be the outermost transformation. The order really matters. And pmap, if you're using pmap, you don't actually have to deal with JIT. It handles JIT for you, which is nice. And now this is really onto in my mind, the killer app, the killer feature of JAX, which is that it's incredibly easy to profile and has great profiling support. So there's a tensor board profiler. There's a guide here in the link. These slides will be shared later on, so you can open up this link that will show you a full execution trace, like timed execution trace of both Python and GPU or TPU functions for an arbitrarily long slice of your program. And what this really can let you do is identify exactly where things are going slowly. And in my experience, that usually doesn't mean the GPU actually. It generally is data loading, environment stepping, data preparation, that sort of thing. Now, if you're in PyTorch and you discover that your data augmentation is slow, there may not be much you can do about it. The good news is that in JAX, if you discover that there's a slow pain point like this, you can just directly use jax.jit on that code to make it faster. So recently I was running a huge number of experiments for data efficient Atari, building off of one of my older papers, and was able to reduce the runtime, just using this profiler, was able to reduce the runtime of the code from about 3 hours to 1 hour. And this was already for a code base that I'd optimized a reasonable amount. It's just, if you really iterate on this, you can dramatically reduce your compute requirements. There's two besides for this. If you're really, you can always parallelize your code to use multiple devices. You can always use FP16 or mixed precision, which JAX does have pretty good support for. But just being able to do things like speed up your replay buffer without having to switch frameworks completely is really, really nice. So I've JITted data augmentation. I've JITted prioritized experience replay sampling, all of this stuff in the past. And I've also been able to interleave replay buffer sampling and training steps without running multiple processes, because JAX supports full asynchronous execution really natively. So there's a lot you can do. And then finally, this is the last slide, just libraries to use for JAX. So the equivalent of PyTorch, like torch.nn, is 2 different libraries, Flax and Haiku. Flax is from Google Brain, Haiku is from DeepMind. They have very comparable functionality. Haiku is a little more versatile, and if you had to choose one to start out with from scratch, I would say to choose Haiku. But depending on, if you're starting from an existing code base, you may get tied into one of these. The good news is they're so similar that you can usually convert code between them in 30 minutes if you really have to, so it's not a big deal. RLAX, this has really good primitives for reinforcement learning. So you can do n-step returns, you can do distributional RL, nonlinear Bellman backups. If you want to do full Lambda, like if you wanted to do distributional Lambda returns in a POMDP setting across entire sequences, and also transform those returns to operate in some sort of squished space, you can do that in a RLAX in like 10 lines of code. Implementing that in PyTorch probably would have taken you a week. So it's a really, really good library. And then if you want more pre-built solutions, there are 2 good ones. Dopamine has good support for DQNs written in Flax. This one is out of Brain, actually out of Brain Montreal. And then Acme is much, much higher performance for distributed RL. So different processes, separate processes for actors, separate processes for replay buffers. The actual implementations in Acme may not be super well tuned performance, like in terms of optimizing environment return, but it will run very, very fast, which if you're working on academic compute, you want to be saturating GPUs because you can't get that many of them. So it's a big deal. So I think I've got 3 minutes left, so I'll just take questions now if there are any.
Hello, can you hear me?
Yep.
So you mentioned something about like only jitting something if you need gradients for it, but then you're like jitting like the replay buffer, like.
No, you should only use jax.numpy if you need gradients, or
Okay.
if you're going to be jitting something. So you absolutely should jit. You should jit a lot of code. It almost always makes stuff faster. Yeah, but unless you're going to jit something, you should avoid JAX functions.
Okay, cool. Wait. So for example, if I were to write a replay buffer, I should write it with regular NumPy, but then still JIT it, or?
No, you should write it with regular NumPy, and then when you're ready to JIT it, like when you've optimized everything else, you should convert every like np dot something call to jax.np dot something, and then apply JIT.
So just like instead of importing NumPy as np, can you just do like import jax.numpy as np? Like, is that?
You totally can, and honestly, that's probably the easiest thing to do. Because they have slightly different functionality in some cases, particularly when it comes to random number sampling, but almost everything else is similar. So you can typically use them as drop-in replacements. I think if you use a regular NumPy function inside JIT, it won't go very well. But if you use a regular JAX, like it just won't JIT it. If you use a jax.numpy function outside of JIT, it's fine, it will work, but it's doing a lot of extra tracing that you don't really need.
There's also another question about given that there's JIT in PyTorch now, is there any other advantage to using JAX? I guess there are two questions about that.
Yeah. So PyTorch does have JIT. JAX has, as far as I know, much better support for a lot of the fancier stuff still. So any fancy optimization is very, very straightforward to do in JAX and is harder to do in PyTorch. I'd say the other reason to use JAX is that the Alphabet reinforcement learning community has pretty much completely migrated to it. So all of these libraries are just here and already pretty fully optimized and will be built on in the future, while PyTorch will be potentially a little bit harder to find support for. But I do think it's reasonable to keep using PyTorch. You're just going to have to make up a little bit of stuff as you go along compared to JAX.
I think that's about it. Yep.
All right, great. Well, thank you, everyone. And I think the slides will be shared later. So,
yep.
Thanks.
Okay. Yeah, thanks again, Max. And yeah, so you around, Jacob?
I am ready to set it off. You guys are.
Cool. Yeah, we can hear you great. And you can probably start sharing your slides now if you're ready.
Cool. Let's just nope, that's not the right button. There we go. All right, so my talk today is going to be a talk in two parts because my initial talk was not enough for the full time. So we're going to talk first about making custom visualizations for RL, and second about using what you got on a particular machine, saturating the GPUs, CPUs, etc. So I'll try to do about 10 minutes for each part and then leave 10 minutes for questions. All right, so let's dive into it. So the thing that I'm going to be evangelizing today is called Streamlit, which is a library for active visualizations, the type of thing you can get in JavaScript. So this is sort of like an alternative to WanDB TensorBoard, but it's less of a comprehensive all-in-one experiment management thing and more of a ad hoc tool that you can use on a one-off basis to visualize exactly what you need to visualize. The fact that it's written in Python is huge because you can basically use all of your tools that you're comfortable with, right? You're using like pandas, NumPy to do all the manipulations of the data. And you can pick your favorite out of the Python plotting libraries like you might have in an IPython notebook. I like Bokeh, but you know, whatever you prefer is most of them are available. And this is huge, is you can directly invoke your neural network. So if you've like trained a policy or something, as we'll see later, you can run that in your interactive visualizer tool. So this, to me, sits somewhere in between an IPython notebook and a like a TensorBoard type experiment management platform. You're sort of getting the best of both worlds, but also like a little bit of the worst of both worlds in that like it's manual and a little bit jankier. But for me personally, it's exactly the happy medium. So I recommend everyone at least check it out. The learning curve is not very steep, and I find it to be really, really helpful. So you know, that's enough words. Let me actually just show you a couple examples of what I mean to maybe inspire you as to why this thing might be useful to you. So over here, I got some demos that I've made. Is this visible? Is this, yeah, looks good. So this is the simplest thing, right? This is just literally, I'm plotting my training losses. So in my code, I've written some losses to CSVs, and then those CSVs I can just load in and turn into this. I'm in a browser here, as you can see. And so if you look on the left, you see these like menus. These are tools, right? Like these are a bunch of different experiments that I ran. These are the different names. I set up this thing, so I have this menu where I can click on stuff I want. Smoothing, again, I implemented by hand the smoothing algorithm, so I can change, I can adjust, right? Less smooth, more smooth, right? I decided, hey, maybe I want to view it as a log plot. So I just put those things in there. It modifies the graph occasionally. I can view different things on the x-axis if I want to say, hey, like how did this go in wall clock time, right? So it's all just like very nice amount of customizability. It's really easy to add new features here, just as natural as it would be in like a Python script or IPython notebook. And then the plot, so this is a bokeh plot, which means I can like, you know, I can do stuff with it, right? Like I can move it around, I can zoom in on a region and focus in more. So okay, this is all pretty basic. This isn't like that big of a step up over something like TensorBoard or WanDB, although it is nice to have a little bit more customizability. But then let's say we're doing some self-play, right? So this is a little self-play algorithm. And we want to visualize how the different policies that I'm training are playing against each other. So I created, this is like a completely custom visualization. You're not going to see this in TensorBoard because it's like very specific to my, I mean, not super niche, but reasonably niche use case. So this visualization here, right? Let me turn off the smoothing. You can see what I really have is a bunch of individual games. So each of these dumps represents a game. I can mouse over it and see the outcome. So in these, I should mention the x-axes are basically how much training the particular model has received. So the player 1 has received more model as you move to the right. Player 2 has received more training as you move up. So what you would expect to see, if all is going well, if the training is helping it learn basically, then player 2 should be better than player 1 when player 2 has received much more training than player 1. And when we mouse over here, you see, yep, like in this game, player 2 wins 45% of the time, player 1 wins only 6% of the time, and there's 50% draws. If you look down here where they're evenly matched, you see, so okay, now I'm gonna turn my smoothing on, right? Again, this is a custom function that I wrote that basically just, in pandas, it's like a pandas group by, groups a bunch of these guys into a single square and then visualizes it. So now when I mouse over, I am like getting a summary statistic, and you can see this very nice like gradual transition to yellow, which means more player 2 win as you go up. There's gradual transition to blue, which means more player 1 win as you go to the right. Pink means they're about even, and gray means there's a lot of draws. So basically, like, this is just a custom visualization that I put together. I'm not suggesting that you use this exact custom visualization. I'm just showing how, like, there's this thing that I wanted to see, which is how are my agents battling each other over time in this sort of like self-play tournament. And I had some idea for how I wanted to visualize it, and able to do it easily. And now the most complex thing that I have, this is a Atari agent trained to play Pong. And I have all the information I need on the run right here. I've got a choice between like which policy collected this data. I can then choose like many different episodes were played according to this policy. I can choose which episode I want. It'll load in the episode, run an agent. I can choose which agent I want to run. I can see the exact, like, this is the frame that the agent is seeing, right? I can look at different frames. So frame 237 now looks like this, right? You're in a different position. I can see the returns from this frame for this episode. What action was chosen on this frame? Reward, the target. I can, over here, you can see this is basically a plot of this episode, the different rewards that occur. So the black line, or sorry, the returns. The black line is the return. So with a discount of 0, we see it's very spiky, right? These are basically the instantaneous rewards received. If you go discount of 1, now this black line is more like a step function, right? Because you start at -21, and every time you lose a point, your cumulative return from that point gets closer to 0. You can look at stuff in between, right? So again, not saying you should use specifically this, but imagine how useful this is when I'm debugging my RL agent. This thing right here is for the particular agent that was loaded. I'm plotting for each action available in this environment. This is the different probabilities of action selection that my policy head is taking. And these are the different Q values that are predicted by my Q value head. And this, I mean, so this run is like, I just spun up a quick run. I didn't actually train very much. This is like 10 minutes of training. So the blue line doesn't show anything interesting right now, but it's basically plotting my optimal Q values according to the policy at various points in the episode. So I can see, does my predicted Q value match up to the actual return that I see? And in this case, it obviously doesn't, but that's because it's not very trained. Anyways, the point is, this is like a super cool, super flexible way to figure out how you want to view stuff and then just code it up in Python so you can view it. I guess one other thing, I can just briefly show my code. I'm not going to go in detail here, but it's just regular Python code. Again, there is a tiny bit of a learning curve, but I'm doing stuff like torch.load policy on device. So I'm literally like loading in a saved policy just like I would do if I was doing an eval run, except I'm using it in the context of my visualization to make a prediction on the specific frame from this specific episode that I'm looking at, right? Okay, so that is mostly part one of my talk. I think I had one other thing that I wanted to say, actually. Oops. There we go. Which is, okay, so what does Mila want to do, or like as a SysRL, as a big lab? Glenn mentioned that we should bring this up. So this is basically my thoughts, is that when I am making my Streamlit visualizations, I often reuse huge chunks of the code in various places, make a few minor tweaks for the specific project or visualization that I want. So my suggestion is that we have a shared repository of Streamlit example code. Also maybe a library of common utilities that get used in the examples. And the idea would be, if somebody wants to make a visualization, they can browse all the different Mila visualizations, see the one that is like close to what they want, and just yoink the code, tweak it to fit their specific use case, and they're done. This is going to serve a similar role sometimes to like a WANDB, but it's orthogonal, right? I'm not really suggesting here that we create a single Streamlit interface for everybody to use. I'm suggesting we create some example Streamlit interfaces that people can modify it into what they actually want to use. Let me check my time. We're looking good. All right. So that is part one. Now we're going to part two, which is using what you got. Oh, wait, sorry. I just noticed in chat there is a question, which is the kind of plot that lets you move things around. I'll just type the library here. It is bokeh, which is just, it's like a matplotlib alternative, but I like it better. It's got a nice interface. It's pretty fast, and it lets you do things like make the plot itself interactive. So, okay. What do we want to do with deep reinforcement learning, right? There's basically two tasks, which are, we want to perform gradient updates to improve our policy, and we want to interact with the environment to collect more data. And in both of these things, we basically, the most important thing is we want to saturate the GPU, because that's sort of the most expensive resource. So that's the one we care about saturating, but we also want to utilize our other resources, which are our CPUs, RAM, and disk. This is sort of a standard setup. If you have more resources than this, then what I would usually do is do DDP, which is basically making, like, you have n GPUs, you make n clones of the entire thing, and then just have the GPUs communicate with each other. So basically, each one of those nodes, you still want saturating the resources that it has, which are going to be the ones listed here. So let's just briefly go through how to do this. So we've got two things, right? We've got learning and interaction. We want to perform gradient updates, and we want to interact with the environment. Learning is basically the same. I mean, the algorithms are different, but the computational saturation considerations are basically the same as supervised learning. So this is pretty familiar. For a small replay buffer, for example, this is what I think dopamine does. Like a replay buffer of 1 million Atari frames is going to fit in your RAM usually. So, oh, by the way, I forgot to mention, there's this color coding. So things on GPU will be in blue, things on RAM will be in purple, and things on CPU will be in green, things on disk will be in purple. So for small replay buffers, we can keep the replay buffer in the RAM, which means you can directly sample a mini batch out of RAM very cheaply. You want to promote it onto GPU, put that mini batch of now like a mini batch on GPU into a queue. And then at some point, when the learner is ready for a new sample, it'll pop off of the queue and process, right? Like, for example, the PyTorch data loader, actually, so yeah, so this is like a basic way to make sure the learner is saturated, because there's always something in the queue already on GPU ready to be processed. For big replay buffers, you might want to put the replay buffer on disk, which means you want to do something closer to the PyTorch data loader loading a data set, where you're going to have many different CPU threads or CPU processes even all hitting the same replay buffer, sampling individual data points. You're going to put those things into a CPU queue, which then, once enough stuff is there, we'll compile it into a mini batch and send it to the promoter. That will promote it onto a GPU mini batch and put it in a second queue. And then again, the learner will be sampling from this queue. So once again, the goal is to saturate the learner by having this queue always have something in it And as long as you have enough different guys popping stuff off the replay buffer, you can almost always do that. Okay, now interaction. This is the part that's more unique to reinforcement learning. Interaction is going to be this back and forth between policy and environment. So for really tiny networks, like for really simple policies, you can get away with putting them on the CPU. But in practice, like I feel like that's not like a good code design decision, because at some point you're going to want to scale, right? The deep reinforcement learning, you're going to want to scale. So I think it makes more sense to set up the code with the assumption that the policy will be on the GPU, right? You'll be needing to, you'll be needing to use the GPU to choose actions. So because you're doing that, we want that sweet mini batch parallelization speed up that we get from giving the network a whole mini batch of things to process at once, which means we need vectorized environments or like a bunch of environments being run in parallel. This is a basic loop, again, pretty straightforward. I'll start at the environment, sure. So you have like 100 copies of the environment. Let's say you have a mini batch size of 32. You have 32 copies of the environment. Each of them have their own state. Each of them send the state to a promoter. Once the promoter has received all 32 states, it combines them into a state mini batch and promotes it to GPU, sends it to the policy. The policy produces an action for each thing on the mini batch. Then the down promoter moves it back to CPU and splits it, sending each action to its corresponding environment. Environment takes the actions, and etc. One important thing to note about this process is that this does not saturate the GPU. It basically cannot, because the GPU is always waiting for the environments to set, right? Like let's say it takes 1 second to do all 32 environment steps. It can be sped up obviously by distributing it across more CPUs, but whatever. Point being, like, we're gonna always be waiting for this environment step to happen. So there's no queue here, like there's no opportunity to queue here. There are ways that could be done, but we're not gonna go into them because what we see is when we put it together, we can do both at once, right? So the interaction loop by itself does not saturate the GPU because it's waiting for the environments. The learning loop by itself does not saturate the CPU because the data loading is generally much faster than the learning. And if this is not the case, you need to optimize your data loading. When we do both of them in parallel, we can figure out how to saturate everything with possibly some spare CPU cycles left over if the environment is cheap. What this means, basically, this summarizes here. We want to choose our actions while loading data from the replay. So this is the interaction on the GPU. Learning is using the CPU. Then we swap. We update our parameters, meaning like we actually do our forward and backward paths in our gradient step, meaning we're using the GPU for learning while transitioning in the environment, meaning we're using the CPU for interacting. And because we're doing both these things at once, you actually don't even need to be super careful about like going back and forth with them. You can kind of just do them both asynchronously, and all the resources just get claimed when they're needed, and basically everything gets fully saturated. All right. And the last, oh boy, what's going on with my transitions here? All right, last thing is just the stuff that Mila might find useful to have as common resources. The main thing is vectorized environments. This env pool thing is pretty good, but I've never set it up myself. I think it would be really cool to have just like a Mila consistent code base that makes it really easy to load things like Majoko, Atari, like the heavy hitter environments in vectorized format that makes it really easy to incorporate into a code base. Maybe you could have some sort of shared framework code for deep reinforcement learning that saturates. There's a question mark on that one because realistically, I would never use this myself, but maybe other people will find it useful. I'm not really sure how much value this has directly. The point of this talk was just to give people a sense for how, like, basically, like, you know, it's not that complicated. It's just like, this is, if you want to write code that fully saturates GPUs, then this is how you do it in RL. It's just like a slight tweak on the regular thing that you do for supervised learning. I should mention that a lot of existing libraries don't do this. Like in Max's talk, I think he mentioned like dopamine and Acme. Acme is much faster. That's mostly because it's much closer to do. It does this parallelization stuff. It's much closer to saturating the deep RL workflow, whereas like dopamine doesn't at all. Dopamine like does some steps, just like 4 steps of learning or something, and then a single non-vectorized environment step. So it's really slow. I mean, it's a good library for other reasons, but it's not a good library for research utilization, and is like probably could be made 2x to 3x faster if these changes were made. At least this is as far as last time I looked at it. Maybe they've improved it since. And yeah, that is the end of my talk. Happy to answer questions. See my time is. Oh, perfect. All right. Yeah, 10 minutes for questions.
Yep. So what do we have here? There are any questions though.
It's
does
tough for
anyone
me to
have-
hear you. Yeah, just ask in the chat or at the mic or whatever.
Hey, thanks for the talk. Quick question. You talked about this idea of maybe creating a kind of framework or something that just does RL and saturates the GPU at Mila or something. I was wondering, do you think that it's maybe a good first step to make a single project that does that, like a simple kind of template thing that you can tweak and just make it available so that we have like an example that saturates and then people can just tweak it for their own use case kind of?
Yeah, I think that's a good idea. I mean, I'm always like template over framework, or like template plus library, I think is a really good combo, versus framework, I feel like is way too heavy-handed, and I never use. But yeah, I think like a good template project could be super useful. Just for showing people like giving people something to build off of, basically. I have never actually used Acme. Maybe if somebody else has used it, they could comment on it. I have basically never used any library, any libraries, to be honest. I have only like rolled my own, so I can't really comment on how that works.
I guess I wanted to ask sort of a somewhat similar question, because at the end you said like you always end up writing your own code and that you're not sure like a framework based on this would be very helpful. But like, for example, I'm pretty sure we all use NumPy. We don't end up re-implementing that for everything we do. So how can we get some form of a framework, I guess, to that level where it's like we don't even question what's in there. It just gives us a function that we can use. Is that the level we need to get to for easy adoption?
Yeah, I think it's challenging right now because the research is so, I mean, it's so researchy. You know, it doesn't feel like there's a reliable subcomponent of RL that I wouldn't maybe want to tweak. You know, whereas with NumPy, it's like, okay, I'm not messing with matrix multiplies. That's pretty locked in. Like we're multiplying matrices. We're doing it this way. These are the algorithms. Like I'm not gonna try to tweak how I'm doing matrix multiplies to improve my machine learning. Versus, yeah, RL. Like so, even the library like Torch, right? Like we just had talk on Torch versus JAX. That we're getting to the level where actually maybe there are different ways we want to do differentiable programming. But once we get to RL, I feel like it's complete no man's land here, as far as, you know, people are still trying so much different stuff. My sense is it's very hard to pin down one thing and be like, this everyone's going to need, everyone's going to want to do it this way. We can just make a call and hide it from users. So.
Okay. Do you think there's at least one thing on the top of your mind that you think could be included into a library like that? Surely not every single part of every RL library is up for debate and could be modified.
Sure. Okay. I mean, so one thing that I think could be helpful is a replay buffer that does everything you could possibly need out of a replay buffer. So this is another thing where I keep having to roll my own replay buffers because I need slightly different things out of them. The biggest thing here, honestly, is we want something that lives on disk so it can be scaled arbitrarily, is very fast to sample from, so that, I mean, yeah, like there's a lot of ways to just do like naive stuff on disk that then becomes way too slow to sample from, such that you can't possibly collect your mini batches fast enough, and has functionality for things like, you know, you want to store observations. For example, you don't want to duplicate Atari frames, right? Like if you have 10 frames in a row of Atari, you don't want to store, but your algorithm is using a 4-frame history. you don't want to be storing copies of the 4-frame history in the replay buffer, right? That's very redundant and wasteful. You want to only store like one roll, like one the whole episode 1 frame at a time, and then just be slicing it in chunks of 4. And then you also want to be able to have this thing be like a sync for multiple writers, because if you have multiple actors, you know, interacting in parallel, you want them each to be able to write to the replay buffer in parallel, and you want to also be able to read from it in parallel. So there's just like all these features that sort of are strictly good and require serious engineering to get right. So I think a really good replay buffer that does all that stuff would be a very useful utility that could just be universally used anytime somebody wants to do that.
Thank you.
All right, yeah, anything else, or good call here? I guess we got only 5 more minutes, but take a little break.
Did we take 5 minutes? Did people want 5 minutes break? Okay.
Cool. And as always, feel free to like message me with any other follow-up questions. Yeah, thanks, guys.
You're nervous or something. It's okay. It will be fun. Like I'll be there for emotional support if you want. Okay. Yeah. Oh my god. Oh my god. Okay, so I should leave this actually.
Okay, guys. My sound is okay, I guess. And for people online, is my sound okay? Yes. Yeah, okay, cool. Okay, so so my talk is very sort of robotics focused, and I don't know how many people in this room are working with real robot, but basically I'm gonna kind of take you through my setup and some of the challenges that I have in my research when I'm doing like sim-to-real kind of robotics with RL. So I'm gonna go over some of the sort of robot arm manipulation benchmarks and environments. which are kind of popular, the ones I use myself. And then I'm gonna take you through like my Sim2Real infrastructure, which is gonna have some brief overview over ROS, which is a ROS, like a robot operating system. And I'm gonna kind of focus on the ARM I use, which is so like JCO Gen 2. And I'm gonna talk about the choice of controllers when you're kind of training these policies with RL. And then just some other topics that you kind of want to consider when you want to kind of train on run like Sim2Real transfer. So these are some of the sort of most common robots that is benchmarks like kind of support. So there's the Canova ones, the Franca, Sawyer, and all of these arms are sort of like at 7 degrees of freedom, which means there are 7 kind of joints where we can kind of move these around. And also like they all come with like different weight, like size and configuration and kind of gripper model. So they have different purpose for different tasks. Depending on tasks, you can kind of choose some of these robots. So then the next part is like the choice of the controller. Like most of the time when people use like Mojoko or the gym environments, you don't really worry about what kind of controller you're using, because typically they're based on like a high level controller. So the RL agent actually ends up just controlling the hand of the arm. So basically it's pretty much just learning how to move a 3D point in the space. But when you want to do work with robot arms, you kind of want to consider what kind of controller do I want to learn with my policy. And these controllers kind of start with kind of low level, going up level, higher level. So like at the very low level, like you control a robot arm with the torque. And that is basically just how much force you're applying to kind of rotate these joints. And then that's like a low level, but typically like you can use velocity controller or position controller. And these are basically just the commands you put to each joint individually. And then like most commonly, like the benchmarks like MetaWord, if you're familiar with these RoboSuite benchmarks, they use like end effector controller as well, or at least they have support for end effector controller. And the kind of like 2 popular ones are just like a classical IK solver, which is basically just it's like a kinematic controller, and you don't need to worry about like how it works, but just that's kind of like a very vanilla end effector controller supported by these benchmarks. And I only know one benchmark, RoboSuite, that also offers the operational space control, which is OSC for short. And this is actually a much better kind of end effector controller, like for contact-rich tasks, because it's also considering sort of like a dynamic based, whereas IK doesn't really consider that. So it actually calculates how much like force the robot can apply to surfaces. Yeah.
IK is first kinematic.
Yes.
What kinds of solvers are typically used to do that?
Like it depends. Like I think all of these benchmarks actually have their own implementation. So you kind of have to look at what the code is doing, but it can be very simple, naive implementation to something much more robust. And yeah, you also, like every robot also has its own implementation, but the OSC, it's more, yeah, it's different. So, okay, so then you decide to train your RL. So then you say, okay, I want to learn a joint position controller because that's maybe easier, or you can kind of train like an end effector controller where the policy doesn't have to worry about like how to configure the arm. Like it only worries about moving the hand, and then the rest of the controller will handle the rest. So then you might get different behaviors depending on what kind of task you want to solve. So all of these tasks are actually accomplishing the same thing, which is reaching this ball, but they're kind of different configurations. So I'm going to very quickly go over some of these like benchmarks that I use, like MetaWord, RoboSuite. This is more like a reference if you need to kind of check out these environments. I don't really have time to kind of go over in detail, but like the main point is if you do want to like do with kind of Sim2Real robotics, so like you have to consider whether these benchmarks are actually have like realistic physics or non-realistic, because that kind of matters if you want to run your policy on a real robot. So for example, MetaWord was never really intended for sim-to-real, like it's mostly just a Sawyer arm, like end effector controller. And it's really mainly for like multitask learning and learning these tasks. Like it was never intended for, so some of the actual like movement and collisions are not very realistic. So it may not work well on a real robot. And then there's the computation and how much reward engineering they've done. Like some of these environments, when you train like a task, it might not actually be solvable. So you have to maybe go and change the reward function and apply more reward engineering. What kind of tasks they have, like, you know, if you want to run a real robot, like ideally you want to kind of be able to run that on a real environment as well, and how extendable they are. So if you want to like quickly out your own environment, how easy it is. So another note with when you want to do like sim to real, like there's a popular domain randomization. And this is like the first thing is dynamics, because if you're if you train your policy just in simulation and then real arm, the dynamics are different, your policy is not going to transfer. Based on my experience, like usually these models are actually very realistic, so that when you just run on a real robot, it works. But depends on the task. Like for easy tasks, if you have more challenging tasks, you can apply like, and domain randomization basically just means that you're kind of varying like the physical properties of your robot, like friction, stiffness of the joints, and the policy is exposed to all these variations. So then it can also works on the real arm. And RoboSuite, which I'm kind of mentioned, that which is mostly what I use now, like already supports this, so you can just switch it on, and then it's just gonna domain randomize everything. And then the visual domain randomization as well, if you're doing like pixel-based like policy learning. So there's a color, texture, lighting. So just one warning, like RoboSuite actually does on-the-fly randomization. So as you're like, you know, training, you just switch it on. And then, yeah, so at every episode reset, it's just gonna apply. So it applies a lot of randomization that actually, it hurts the policy performance. So usually what works best in my experience is like, when I did the customization myself, like I had this fix. So during the whole training, so for example, we had like 20 variations, but then the policy can actually train in that domain better. And then it can also apply viewpoint randomization and things like that. And RoboSuite already supports all of these as well. So this is kind of like the customizations I made, like in my paper, like we just had this meta world, like, you know, I'm just like randomizing different variations with the hope to generalize to like unseen or to the real. And the bottom one is like a DM control, and DM control also supports these manipulation tasks. I see a lot of tasks in their paper, but it's not really on the DM control like environment. You kind of have to dig in, and because it's a bit varied, so it's not commonly used, but it is available with this JCO arm as well. Just very quickly about Isaac Gym. I'm only mentioning this because so Isaac Gym is kind of made by NVIDIA, and basically it's, I'm not gonna go over the details like why it's so fast, but it's super fast. And they have a very good, like a kind of like a sort of like a, so basically everything is running on GPU. So all your environment steps and interactions, everything is happening on the GPU. And then you are actually, you see in the photo, like there are a lot of arms. So all of these are training in parallel. So you can actually train like 2000 instances of your robot in parallel. And just all that to say that actually PPO with like Franco cabinet, you can train it in 5 minutes. So it's really nice when it works. So the only thing is like, I don't know, I think it's getting better, but when I was working with this, like they didn't really, like it's supposed to be like a replacement for or alternative to Mojoko, but they don't have an official like RL support, like a gym on top of it. So what they provide is just examples. You can kind of go and build your own examples. So that's one issue that I think, but they're adding more and more environments. So I highly recommend you check it out because it's very fast. And one other issue, I guess, it was like, it works better with on policy than off policy because I think there's a lot of data coming in into a replay buffer. So you also have to consider that as well. So then there's also multimodality. So maybe now we want to like not only use images. So there's also additional kind of type of data available with RoboSuite. I don't know about other benchmarks, but you can also use surface normal, segmentation, depth images, and so just more information, which is going to help if you want to kind of do sim to real transfer or generalization. And then I'm seeing more papers, like people are just adding like microphone and like tactile sensors are becoming more popular. I think some companies are investing more in sort of sensory, more sensory input. And this is what the tactile looks like. So basically as the arm is touching stuff and manipulating, you can see the data, and acoustic data, you can also kind of take that. And, you know, if you're trying to insert something and then it's not working, you can actually hear the sound feedback. So this kind of some things people are doing in robotics. You can do like multi-modality learning. Okay, so I don't know how many people know about ROS, but basically ROS is an open source, it's like an operating system for robots. It kind of provides some like abstraction, like hardware abstraction. You don't have to worry about a lot of things when you're working with a real robot. It has like low-level device control, and it's all message passing between processes. And it's at the bare bone, it's actually very minimalistic. But it provides a lot of package management for you. And it's also language independent. So if you have something very computation extensive, like your algorithm, like uses a lot of, you can actually implement in C++. And then you can have another process in Python, and these can easily talk to each other. You don't have to implement any kind of bridging between languages. So it's basically just a graph, peer-to-peer network of processes, and their main concept in ROS are kind of nodes, messages, topics, and services, which we're going to talk about. So basically, a ROS node is a software process that performs some computation. So this can be a sensor processing, actuator driver, it can be algorithm, it can be your RL, it can be anything. And basically, this just reinforces its modularity, and then as a good kind of sort of like it kind of forces you not to put too much overhead on one node. So then each node is responsible for different tasks. So if you're working with self-driving cars, you know, if your camera node happens to crash, so hopefully you don't put all the other computation on one node. So then only your camera is missing, everything else is still working. So that's kind of the idea of the architecture. So then there's the concept of messages. So all these nodes are going to talk to each other through message passing. So a message is like a strictly typed data structure. So basically, this is an example of a message of a point in space. So it's X, Y, Z, and you kind of define these. And then each node is gonna kind of like do the data exchange between nodes in a like a publisher subscriber pattern. A node sends like a message by publishing to a topic. And then another node can actually go and subscribe to that topic and read the data. And as you're working with your robot, like, you know, the robot says, hey, my arm, like, you know, I'm right here in this state. It's just publishing all this information. And then another node can go and read all this data. So you can also do like concurrent publish subscriber, and it's like TCP/IP, just like a details, which is maybe not so important for now, but, and services are just like another way of communication. Anyway, and then, so there's a very important concept when you're using ROS, which is like a master. So master provides like a name registration for all the processes, and basically it's kind of like a DNS for all these nodes to find each other, to be able to communicate. So that's just something you learn when you start using ROS. Another important tool is when you are doing this sort of like working with these robots. So this TF library is just basically a transformation between the coordinates, and it actually allows you to kind of debug and visualize. And this is very important because all these kind of meshes are designed so that, you know, they all have their own like a, you know, local coordinates, and sometimes you kind of need to visualize to see what's happening with your robot, if it's not moving properly, or how these coordinates are set up. So then there's RViz, which is another super helpful for debugging, which I use all the time. So basically, when you have your robot, you kind of plug it in, and then you don't know what's going on. Like you need to visualize to see how it's moving in space. So with RViz, you can actually like, you know, you can visualize your robot mesh. And then you can also visualize all the coordinates, like how the initial coordinates are set up, how it's moving. And you can sort of basically just visualize all the data coming in order to kind of debug whatever you need to kind of see visually in the robot. And something else that I think is important to know is how these meshes are actually described. So this is by the what's called a Unified Robot Description Format, URDF, which is the ROS format. Most of the time you don't have to worry about this, but it's just once in a while, like, well, if you do want to like create your own sort of like a robot mesh, you have to worry about this. Like, it's just an XML descriptor for how these joints are connected to each other. And basically like all the initial poses and how like these joints and links are connected. So for example, sometimes like you may have to kind of go and change something in order to kind of in your descriptor if something in your and the robot doesn't match, like some initial poses if you want to like change something. But with Mojoko is actually MGCF, which is actually a different format. So sometimes if you load like a URDF model onto Mojoko, it may not immediately work. But this is just for the modeling basically. Okay, so now I'm going to talk about like my setup that like I've been working with my robot with sort of RL, and then I'm gonna like all the code is open source. So yeah, so if you decide to kind of like work with these sort of robots, you can actually check this out. So I'm gonna use this Jco arm as an example. So basically the Jco comes with the like a Canova ROS. The company provides you the sort of like a ROS package, which is like an interface for talking to the robot. So in theory, you just take the robot out, you connect the USB to the computer, and then it's good to go. You can start talking to it. And so my library kind of provides the method for converting like these sort of standard RL update functions into ROS commands. So then your RL can actually command the robot. Again, it's, the details are not super important, but just as an example, it's like a TCP connection that, you know, connects to the robot arm, and it provides all these kind of typical RL functions like initialize, step, reset, go home. And yeah, and then, so another thing is like, you understand when you use ROS is actually just installation of ROS is annoying sometimes. It can break the computer, and it's mostly supported in Linux. So I've never really used it with Mac. But we also have this like a Jco Docker that you can actually just install and use it, and you can just run this Docker on any computer. You can even run it on the cluster or anywhere. So it just makes it a bit easier to have this sort of abstraction. So I guess there are basically three pieces. So the Canova ROS sitting on top, and then the Docker, and then the interface, which I'm going to talk about it in a second. So yeah, so basically I also modified the RoboSuite benchmark in order to support this sort of wrapper, because RoboSuite was built with the idea of a sim-to-real transfer, but they don't really like, you still have to write like a wrapper in order to kind of, yeah, to talk to the robot. And this also includes some coordinate transformation to convert from sim and real. And this is another problem you might run into when you run sim to real is sometimes when people build these benchmarks, they didn't test on a real robot. So sometimes they got some things wrong, like maybe the robot wasn't oriented correctly or some coordinate transforms were wrong. So so on the high level, this is the kind of architecture. So with any ROS program, you have the ROS master on top, and then you have the Canova ROS, which actually comes with the arm, and then you have the robot arm, and maybe you want to plug in a camera if you want to do like pixel-based learning. And then you have this kind of Jco robot interface, which is basically talking to the Canova ROS. So the Canova ROS is actually publishing all these topics about the arm, about the state of the arm, what it's doing, what's the states of each joint. And then the Jco robot is actually just kind of reading those topics, and it's actually sending commands like I move the arm. And this is then with a TCP connection with a sim-to-real wrapper. And a sim-to-real wrapper is basically just on top of a RoboSuite, and it has like a simulator and a real. So as your policy is kind of stepping, is actually stepping in a simulation and the real. So then you can compare how these two, and then basically, yeah, it kind of exposes all this typical RL functionality for the RL agent. So yeah, basically just like a little bit of code. Like it's very simple, I guess. I mean, if you're using simulation, then you can just use a real robot, and it's pretty much the same thing. You just like with RoboSuite, you just tell it what task you want, what robot you want, because they had all the robots that I showed in the beginning, the horizon. Control frequency is very important. I'm going to talk about a little bit about it, and then the kind of controller you want to use. And then basically you just create your sim environment and the real environment, and then you just treat the rest as like a typical, RL loop. So yeah, so Canova ROS supports velocity, torque control, and joint position control. I never use velocity or torque control because they're a little bit, I would say, position is much safer on a real robot because the torque is very low level, so you can have kind of dangerous motion sometimes. Joint position control is like the easiest thing to transfer. This is something I always start with, like when I want to debug something, like because joint position just works because it's just like all the angles of the joints. So it's very easy to transfer a joint position policy as well. But then ideally we want like Cartesian position control, which is just basically the end effector control, EE for short. And again, you have to like check your the simulation and the real, like all the degrees, and make sure these are all in the same unit. So here, like with ROS, it's all in Euler angles in XYZ order. So you have to make sure all of these match in simulation on the real. So yeah, and sometimes you have to kind of convert these coordinate spaces between the two. So you have to do it. Yes. No, they might have like, yeah, you still need your own RL. Yeah. Yeah, I don't know if I think they had some sort of benchmark and some algorithms, but actually the Compost Suite, I didn't talk about Compost Suite, but I actually recommend people checking out Compost Suite because a lot of the tasks on RoboSuite are not solvable. Like even you train it, it doesn't learn, because I think they tested a lot with imitation learning. But Compost Suite actually is built on top of RoboSuite, and they're using PPO. So they do have like a code that already trains, and a lot of tasks are solvable there. So okay, so when you switch to these sort of high-level controllers, yeah, so they have to make sure, ideally, when you use any high-level controller in simulation on a real robot, you should just use the same algorithm. It kind of makes sense because the controller is the logic that's gonna move the arm, and the policy doesn't have to worry about how to move the arm. It just cares about solving the task, depending on the task. And so basically, like in my case, I'm not doing this, but because they actually Canova with the arm, like actually all the code is not really accessible. So they just have like some algorithms for end effector control. You can kind of use it as an API to control it, but you don't have access to the code. So on the simulation, I'm using a different controller, and this, like, we have to make sure the controllers are in sync. So there's another step of controller tuning and making sure these controllers behave the same in simulation and on the real. So another problem, like I had, like, because these controllers are not necessarily the same, so they don't lead to the same configurations, because both the controllers' goal is to move the hand to some position, but it doesn't care about how the arm is configured. So there might be some mismatches, and this is a problem if you're learning like with pixels, if the policy is trying to learn from pixels, or even like low-level states. You cannot train a policy with low-level state anymore because they're not gonna match. Okay, just another detail about controllers, like, you know, in control, like robotics, we have open loop control, closed loop control. So this is another problem that it comes in sim to real, like because in simulation, actually things are closed loop, so everything is happening very fast. There's no error accumulation, but on a real robot, you have a real physical robot, and the controller needs this sort of error accumulation in order to kind of calculate the next step. So there's more delay. So you have to make sure all of these are kind of synchronized. And RoboSuite by default, so basically RoboSuite controller will execute several iterations of the execution, like in sort of at some certain frequency. So by default, I think it's 20 hertz, but this doesn't work on a real robot. Like you don't want to run on 20 hertz, that's way too fast. So you kind of want to lower it down to 5 hertz, and then you have to like then tune your controller in simulation to make sure. Yes.
Why is it too fast? Isn't faster better?
Yeah, but on real robot, it won't move that fast. Or at least it's very hard. Like if you make it that fast, like it's very hard for the policy. Yeah, because basically in real world, we have this limitation of the arm moving very slow. So you have to make sure.
So this is for actuation. Sensing.
It's basically just how often you're running your controller loop and applying the actions and waiting, because the controller is like applying the action and then it says, okay, where am I now? Am I there yet? So, okay, I have to correct myself. It's like a feedback control loop. Okay, so this is some of the sim2real research reacher tasks that I run. So, so this was trained with DM control. This is joint position control. And basically, I do zero-shot transfer because I don't want to train on a real robot. That's too scary. So hopefully, like my research is basically like, okay, I just want to train in simulation and I just want to run it on the arm, on the real arm, and hopefully it should work. So this is for reaching. Reaching is actually very easy. Usually, it's just like it's like a unit test for it's like my unit test when I want to like run these tasks. And this is like a cube pickup. And the goal of this actually is generalization, because it's supposed to ignore all the background and not care, and zero-shot transfer with pixels. And the task is basically just grabbing the cube. And this is just some of the random tasks I made with Isaac Jim. Again, like I highly recommend people check it out because it's super fast. I'm not sure if it's RL ready or it's easy to train RL, because actually at the time I was working with this, they were only testing with like a one implementation of PPO. So it felt like they were actually kind of overfitting to PPO with these tasks. So, but it's very nice and it's very fast. Yeah, so these are just a bunch of other tasks like I solved recently, like pick and place. Pick and place again, like yeah, you need to do some reward engineering. So it may not work out of the box, and the Sawyer and the Panda with the door opening. So all these tasks are solvable with RL. I think it takes about, I don't know, maybe a few hours. With pixel-based learning, it takes a bit more time. But yeah, so I guess these are all the resources. And yeah, if you have any questions about this sort of frameworks or about the code, and feel free to reach out. Yeah. Yes. So could you repeat the question? Oh, yeah. Yes.
So your RL agent is outputting velocity positions, right?
Yes. So it depends what is. So so basically all this data is coming to the RL agent in terms of the state of the robot, and the RL agent is actually just outputting the action, and the action depends on what controller you picked. So if it was joint position controller, the RL is actually outputting the location, the position of each joint. If it's end effector, it's just the position of the end effector and the status of the gripper or the fingers.
And then afterwards, you rely on that information on controllers.
Yeah. Yes, Gloria. Actually, it's better if you come to the microphone so people can hear you. I think that's how it's supposed to work. Yeah, because people online. Okay, because is it not on?
So what did you tell a ML research, a reinforcement learning researcher who's never touched a real robot before and who might be super intimidated by all of this?
Was it intimidating?
I'm like playing devil's advocate here for a person who, like, obviously there's a lot of like infrastructure that goes into setting everything up. But once everything is set up, like it is in your case, and ROS is running in the background, how hard is it to actually do a transfer?
Like it's super easy. So like you should all do robotics. No, but actually, like no, it's actually a bit annoying because so my experience with these benchmarks, like I mean, okay, I see more and more people putting out benchmarks like, oh, here's the benchmark of this and this, but most of them don't work like robustly enough for me, because even RoboSuite, I had to actually fix a lot of things because they never tested on a real robot. So, and there are always like problems with like, yeah, you run into problems, basically. You run into a lot of problems, but I think it's getting better. I think more and more people are kind of interested in Sim2Real and making this software better. I mean, even RoboSuite is great because I think it's like, you know, a first benchmark that's actually providing so many controllers and so many choices. I didn't really cover a lot, but actually it gives you a lot of freedom for all the controllers. And so, yeah.
I guess I had sort of a similar question, because even on that last slide you showed with about like 15 different pieces of software that you had to use just in the last little bit, like how do you pick between these and like actually go about like, why do you use RoboSuite, for example, compared to all the other ones? And you also mentioned Isaac's Gym. So like which one maybe should we pick and like build on, or
yeah,
is there no
so
perfect
I
one?
spend a lot of time on all of them. So that's why I said, like, when you in the beginning, like if you do want to do work with a real robot, it has to be physically realistic. So Isaac Gym and RoboSuite actually provide better, like more realistic physics, and that is like with collision and all these things. But MetaWorld is like a little bit far off. Like MetaWorld is mostly just for, you know, meta learning, and that's why they made the benchmark. So you have to like just read the documents and make sure. And yeah, so basically, yeah, if you decide to do Sim2Real, you have to read your robot spec and then make sure the simulation and the, so with RoboSuite currently is, I think, is the best for running these experiments because they already have a lot of support in place.
Thank you.
Thank you for the presentation. I had a question about Sim2Real. So it seems like on one of the much earlier slides, it was mostly like sensors in simulation versus in real world. But I guess there's also the whole like actuator side of things. And I'm wondering if you run into different problems on that side and if what kind of solutions you have for things like
that is for the mismatch.
For the mismatch of like, I guess the robot physics, but also like how the actuator signal will produce a different result in simulation and real world. Yeah.
Yeah, actually, like they're pretty good. Like the models, like they have like on simulation and on the real, like okay, the tasks I had is the ones I showed you. So they're not super sophisticated. They're still very simple. But for these tasks, like it works pretty well. The easiest thing is the position controller, and yeah, so yeah, but people usually just sell domain randomization as a solution, which is not the best solution. It's just one way of yeah, just trying out this variation in simulation and then real route, or in a worst case, like you can always just like fine tune on the real hardware. But it's definitely a problem, but it's not as bad as you think. So. And the control behavior, yeah, that's a bit tricky because yeah, you do need to make sure the controllers behave the same. Okay, I think we're gonna. Or disagree with what?
Just Sim2Real seems to get a little harder with the task.
Yes, exactly. If the task is very dynamic, yeah, it's not gonna work well. Like I think with the task I had with the ball, like yeah, I don't want to run that on a real robot. Like. That's too hard.
Hi, thanks for the presentation. I'm wondering, you mentioned in the beginning of your presentation that there are some configurations that are not physically realizable in the ARM, maybe sometimes. So what do you use for path planning in the 7-degree ARM?
So I'm not actually doing any path planning or trajectory planning. Like you could do like all this that the software allows you to do, and they actually have algorithms that do that, but I'm just doing RL basically because I'm lazy. So I just like let the policy learn, and the controller is actually handling like you know, the kind of position you can get into. So yeah, the controller is doing all of that because we're not doing anything low level. Most of the time it's just like high level, and yeah, you don't run into that kind of problems because it doesn't relay you. It just stops basically before it gets to bad position, locking position.
is it possible to make a simulator both differentiable and realistic?
Differentiable
And like realistic?
and that's the question for Florian. Not yet. Yeah, you should come.
So Brax is the closest we got so far to this, and their physics engine, even after, sorry, their collision checking, even after several bug fixes, is still not perfect. So it's still possible to trick Brax into like slamming an object through a table, or your robot arm for that matter. So far it's either or, and for performance right now, my vote would be on Isaac Gym, and for differentiability in a very small controlled environment where you like really like double check everything, I would go Brax.
Thank you. So I think we take a break now and come back at 3:30. Do we take a break?
Hello. Hello. Okay, guys, we'll continue now. If you can, please. Next, we'll have Jesse. He's going to talk about experiment launching and containers. So everyone can take their seats, please. Thank you.
All right. So I'm going to be talking about what I think is one of the largest pain points for me historically. And I think everybody here has probably cobbled together some type of their own framework for experiment launching. And I think there's a lot of room for improvement here. And so I want to go over kind of what my ideal experiment launching framework would be. And then I actually have some progress towards this experiment launching framework. And I have some demos along the way here. So we'll talk about experiment launching. And so what's our requirements for when we're launching our experiments? We want them to be reproducible. And so one of the biggest things with this is the runtime environment. Porting your runtime environment across even the clusters that we have at Mila and Compute Canada, sometimes it can be non-trivial. Sometimes it can be fairly easy. You just need to, I don't know, pip install some file. But at the end of the day, there is a lot of room for improvement here. And so later on, we're going to talk about containers and how this can kind of help alleviate some of this. One of the other things as well is kind of code checkpointing. So I don't know if anybody, maybe somebody's, hit this at one point when they're running on Slurm. You schedule a job and then you go and change your code and your job hasn't been scheduled yet. And then so you change your code. And then when the job actually gets scheduled, it runs your updated code. And then the experiment you intended to run isn't actually run. And then so you have to go back and change things. And so there should be, we want reproducibility across the runtime environment, but as well as kind of when you launch your experiment, you want kind of a checkpoint of your project at that time, and you want it to be able to run just as it was. And so the other thing too, is we want to be able to easily modify kind of the specifications for our job. So typically people will most of the times do this using Slurm, but I don't think we should take for granted that there are a lot of people probably that are gonna, whether they intern at Mila or they're new and maybe they don't have a computer science background and maybe they're not comfortable, writing bash scripts to be able to schedule these types of things. I think there's, most people coming in will probably be familiar with Python. So it would be helpful if we could specify kind of the launch configuration in Python instead of doing this with a bash script. And especially for RL, we're seeing a lot of methods now are going to be kind of distributed. Jacob was kind of talking about this earlier. Acme does a really good job of having this distributed setup. And so we should be able to kind of also add kind of if we want to have multiple actors or we want to have more of a distributed setup, it should be easier to do this than it currently is with Slurm. I bet there's probably pretty few people who have run distributed setups on Slurm. And the other thing too is hyperparameter sweeps. So we want to be able to specify this. It's part of kind of the launch specification, and people have all different sorts of ways that they're going to do this. Hydra has become pretty popular for people to use this kind of a configuration system and a way to launch experiments, but I think it still has some room for improvement. And one of the other important things too that I think should be a requirement is agnostic to the compute environment that we're running on. So we do have access to some GCP credits sometimes, or maybe we have access to some other compute resources, and we're going to have to spend some time to modify kind of our experiment launching to run on these different environments. And so it'd be really nice if there was something that was kind of agnostic across different computing environments. And so with these requirements in mind, I'll kind of dive into a little more of these. So reproducibility, I think that people should start using containers for this. So why containers? Again, they're reproducible. You pretty much get to configure the software stack that you want to run in. And so they're portable. So they'll be agnostic across these different infrastructures that we have access to. And this is also important, kind of ease of onboarding and setup. If we have like an external collaborator or an intern or something along these lines, it's much easier to get somebody onboarded if you have some configuration for a container that they can easily run, rather than having a really long README that is probably error prone in them setting up the compute environment to run experiments. And I guess this also fits into that, just ease of collaboration. And so containers can be kind of a mess. These are a whole bunch of different kind of specifications for container runtimes, container build tools. There's a lot of things that are going on here. And so it's not always the easiest to navigate this landscape. But this is kind of the idealized setting that I think we should be in. So you're on your machine, and ideally, I do not want to touch the cluster at all. I mean, especially on some Compute Canada clusters, the file system can be slow sometimes, and it's frankly quite annoying to have to work on the cluster. And so my ideal setup, at least, is I'm on my machine, I launch an experiment, it builds the containers that I need, it pushes those to some registry, it schedules things on the cluster, and then when my job is scheduled, it pulls things down in the configuration I had, and it runs those things. So this is going to be agnostic across environments. We can do this on Slurm. We could also do this on Google Cloud. We could do this on AWS. There's a whole bunch of different ways that we could end up running things. And so I think this setup here is something that we should strive towards. And there is a framework that kind of allows us to do this already. But one thing I wanted to demo now is it's great and all that we have, these containers that might run on the remote infrastructure, but there's also kind of a specification now for these development containers. So they're containers where your development environment will actually live. And these can be quite cool in some ways. This started off as kind of a VS Code feature, and now it's kind of became this more general standard. So you can use it with like NeoVim and a whole bunch of different editors now. But I think let me see if I can get this to work here. So one of the coolest things too, I don't know if people have probably seen this too, on GitHub, there's these things they call code spaces now, and they work off of these development containers. So you can define essentially what your development environment should look like, and then you can essentially click one button, and in your browser remotely, it will give you kind of this container running on their infrastructure. And with essentially zero effort, I can now develop, I can now launch my experiments, and I didn't have to set up my development environment at all. And this is also the case in something like VS Code here. They have this remote explorer tab, and you can essentially clone into a repository that has one of these development container specifications, and it will essentially set up the container and it will set you up in that environment. And then there is zero setup to setting up your actual environments. And so this is nice in that, again, if you want to collaborate with somebody, it makes it very easy to kind of set this up. And so, well, wait, this might finish. It might not finish in time for me to show this. But the other advantage of this is that if we're actually running in this development container, we can have some guarantee that when we actually schedule our job on the cluster, it's going to run as we expect it to, because we're already running kind of in this compute environment. And so this kind of takes out a lot of the error-prone nature of how we, I guess, currently schedule experiments. I would imagine a lot of people are probably, they probably have some Python installation on their machine, they pip install some packages, and then they develop there. And then when it comes time to running it on Compute Canada, maybe you didn't test it out on Compute Canada, maybe you're forgetting a dependency, things like this happen all the time. And it's just, I guess it can waste some time. And so, yeah, these development containers can be useful to kind of guarantee that what we're going to be running on the cluster will kind of resemble what we were developing in. And so now I want to talk about kind of how we're going to define our launch specification. And so this is going to get into a tool. It's called XManager. It's going to be what pretty much all of Google uses internally to schedule it to launch experiments. They open sourced this tool not too long ago. And so they already have some kind of features built into it that you can schedule kind of containers on GCP and Kubernetes clusters and other things like this. But my goal was to essentially write a Slurm backend for XManager, and it would give me a lot of the benefits that XManager has, and would give me kind of all of my requirements list there. So I'm going to go into a little bit about what an XManager job, how you define it and what it looks like. So there's going to be a couple things that you're going to define. You'll define your executable. At the end of the day, at least in how XManager works right now, this will be a container. And so it's going to be like we're defining some configuration for our container. So it's going to be a Docker container, and then we're going to define also an executor. So it's going to be what's going to actually execute our container. So they have a local executor, which would just execute things locally on your own machine. The Slurm executor is what I had cobbled up that I'll show you later. And they also have a GCP kind of executor as well. And so with kind of like minimal amount of change to your launch kind of scripts, you can run on all of these things, which is very nice. And you'll also define kind of a job, and a job is dependent on an executable, an executor, and then it will have some arguments that will get passed down to the command line, and you can also specify some environment variables as well. And for, yeah, go on. Yeah, so the executable can be defined in a whole bunch of different ways. So it could be just like a Docker container that has like an entry point that will get executed on you know, when it actually gets run. What I'll show you is that you can define an executable for like a Python kind of like entry point. And so this could be like a module or like a file that's going to be run. And so, yeah, it's flexible in this way that essentially it boils down to, it's a container that will get run on the cluster. And so any way that you could define like an entry point into the container, you could do similarly like this. And then as I was talking before, it would be really nice if we could define kind of these distributed setups where you have some dependencies. So in the case where, say, you have like a whole bunch of actors that you want running, and then you have a learner, and these things kind of have some dependency on one another, the actor is going to be sending kind of transitions to the actor is going to be storing transitions in some replay buffer, and then the learner is going to sample from the replay buffer. They actually support this kind of job group. And so a job group is just going to consist of different jobs that might have different requirements, but they're all going to get scheduled together and they'll all run kind of in tandem. And so I'll go into kind of what the code looks like for each of these things. So here's like a simple example from the Slurm kind of backend that I wrote. So you start off and you create kind of this context manager for an experiment, and then you create kind of an executor specification. So this is going to be like where your executable is going to get stored. And so this GHCR, it's a GitHub container repository. And so with any kind of GitHub repository, you can store containers alongside your code there. And so this is an easy way just for my executables to get stored with my code in GitHub. And so the experiment kind of, the experiment object I get back here, there's a package function. It takes an array and you can give it, these are the executables. So in this case, there's a Conda container, and these are, I didn't usually like Conda, but it's actually helpful when you're running with containers. And so there's this, I also have a Python container that you can specify here, but the container, essentially, it takes the executor specification, and then it takes, in this case, I define an entry point. So this is a module to a Python script that I'm going to run. And so what this package function will actually do, it's going to go and like build the container locally on your machine using Docker, and it's going to push it up to this repository here. And so that's what's going to happen with this package function. And you get back this, the actual executable here, the train. And so then you're going to define your job. And so a job's going to take an executable. So it takes the train function, and then it's going to take an executor. So what's going to actually execute this thing? And so the executor, there's other arguments that you can give it here, but you just specify the job requirements you need. So 4 CPUs, 1 GPU, 8 gigs of RAM, and the time that I want to request is 3 hours. And so that's essentially as easy as it is to define a job. And then here's where we'll actually schedule a job. And so I want to do some sweep over some hyperparameters here. The way I have this set up right now is as long as you have like a sequence of dictionaries, these will just get passed as command line arguments to your job. And so all you have to do is call experiment.add with this job, and then give it the kind of trials that you want to run. And it will essentially schedule the Slurm job for you, and it will pull down all the containers for you and everything. And, you know, in very few lines of code, you now have a hyperparameter sweep that you can run on GCP, you can run on any of the Slurm clusters. It's also worth noting that when you're doing things this way, you can actually go out and I can query all of the Slurm clusters we have access to and see what is the minimal kind of scheduling time for these. And I can schedule this job over all of the Slurm clusters we have access to, which might make better use of resources. But there's a whole bunch of cool stuff that you can do when, yeah. Sorry, I didn't hear you. Can you Yeah, so it's just as like flags to your program. So you could use anything, like you could use you could even use Hydra if you wanted to. You could use like any of the configuration systems, as long as they just get passed as kind of command line arguments. And yeah.
If you don't mind going back to the previous slide.
Yeah.
So or the one right before that. Sorry. Okay, so this GitHub container repository, what kind of thing do you push on it? Is it like some singularity container or something that's runnable on Slurm, or is it just like a Docker container and then you manage to sort of make it work on your end?
It's a Docker container, and then when I actually schedule the job on Slurm, there's a whole bunch of bash that ends up doing the right things to get this scheduled and use caches properly and stuff. And so what it's actually pushing to the container repository is a Docker container. And then when it's actually scheduled on the cluster, that's when the, I guess, magic happens of actually executing this. Yeah. So what's actually the actual container runtime that's on Slurm, we use like Singularity, but it's now, I guess, branded as Apptainer. And so it doesn't work exactly how Docker works. I guess the details might not be too important, but you can essentially, so just as Docker has like layers that you would layer on top of one another, to not rebuild the container every time on the Slurm server, I essentially have a similar concept here, because they allow you to essentially overlay file systems on top of a base container. And so you can define what's being masked by this Conda container thing is there's an overlay that's being created for your code and for the virtual environment. And so these are actually overlaid on top of a base image. And so you don't have to rebuild the entire container every time. It's, yeah, most of the time you'll just be changing your code. And so it's really quick to pull things down, and then it just overlays your code on top of the file system. Yeah, yeah, yeah. Yeah, for sure. So this is where kind of the development containers come into play. So you can actually define like you can run the JAX kind of like CUDA package inside of one of the development containers, and it will just work because it'll just default to the CPU version of JAXlib instead of the GPU one if it can't find a GPU on there. But maybe that's not entirely what you're asking here. When you define this Conda container, it'll actually copy, if there's one of these environment.yaml files, it'll copy that over and create the environment from that. You can also specify a custom environment file to this Conda container function here. So if you had like a specific configuration you want to run on the server, you could just pass it a different one of these environment files, and it would essentially build your container with that. Okay. So yeah, calling experiment.add here, that's going to schedule the job on the cluster. And this is kind of just a very high level of what Xmanager is capable of. Like Xmanager can do so much more than this. I think I'm not sure if you guys can see this too well, but this is an example of a job group. So a job group just takes in as keyword arguments, it's going to take in a job, just as I had showed you on the 2 slides ago, I think. And so each job here has its own executable, and it defines its requirements, and these will get scheduled at the same time on Slurm. And so you can easily run, also there's the first job, it has this replicas parameter. So essentially this is going to run 5 actors, and it's going to run a single learner on this, like in a single Slurm job, and they'll get scheduled together. So it makes it super easy to do things like this and communicate kind of between these different executables. And so yeah, there's actually some more examples that are in the Xmanager repository on GitHub, and they can show you kind of some of the other things that are possible with Xmanager. But you can do really cool things like have hyperparameter sweeps with like parameter controllers, and do a whole bunch of really interesting stuff like this. The abstraction that they make over experiment launching, I think, is a really useful one. And so yeah, I guess I'll show a quick demo of what is. Okay, so this is my this is very similar to what I had up here. I probably have to, how do you? Okay, so this is pretty similar to what I showed you guys before. So you have this experiment. I have this. It's going to be uploaded to this container repository here. I'm creating my executable, which is the train executable here. I'm defining. I have just a helper library to define my hyperparameter sweep here. I'm just going to sweep over a couple seeds. I define my job with the executor and the requirements I want, and then that's that. I can go over. I'll probably have to zoom in here too. So I go over here and I can launch that script that I just had, and it's gonna Docker is gonna build the layers for my code, and it's gonna build the base container. It pushes all those things to the container repository to the registry, and then it looks over all the Slurm clusters I have access to. It finds the one that is gonna schedule the quickest, and if everything goes well in the demo, yeah, it scheduled my job, and it tells you when it's going to get scheduled. So I guess it's going to get scheduled close to now. And so, yeah, I guess the reason I wanted to, I mean, I don't know. I think this has always been one of the pain points. Oh, here, this is actually Xcode running in my browser now inside of that development container. And so it was it was a one-click setup, and now I have access to this, and I could schedule my experiment from within the browser. So this makes it really easy for like collaborators and stuff like that to just be able to spin up your code base and then run experiments like very quickly. Yeah, so I guess there's this, I added this slide because some people had said in the first couple slides kind of like, what can Mila do to support things like this? I think that job scheduling is one of those kind of, I think it is a real pain point here from talking to other people. I don't know if other people feel the same. Maybe, you know, people are very comfortable with scheduling jobs, or they've kind of created their own kind of infrastructure to do this. But I think that kind of developing something like this where you have these abstractions would be really useful for Mila, and would allow us to, you know, not have to worry about job scheduling and not have to worry about, oh, it's close to a deadline, we need to run on GCP. How am I going to set up, you know, my environment there? You just have to change a couple lines of code, and now you can run on GCP. And as Glenn and other people were talking about before, you know, if you have, say you're running on a robotics environment, that might be pretty hard to set up on the Slurm clusters, and then you have to set it up maybe on GCP. And so using a container allows you to abstract that away. And as long as you have a container you know works fine, then you can kind of just plug it in as the base image in XManager, and then everything is kind of like layered on top of that, and then everything is hopefully just going to work. But yeah, one of the biggest, I mean, I don't know anybody at IDT, but one of the biggest complaints I have is I don't know, like I'm no container expert, but I don't understand why alternatives to Singularity haven't been, I understand you can't run Docker on these HPC clusters, but I don't understand why alternatives to Singularity haven't been explored, or maybe they have, I'm not sure, but I'm not a fan with how Singularity operates, the paradigm they have there. So I don't know. Maybe I think like this type of workflow where everything is done locally and then kind of just pushed up to some registry and then pulled down on the cluster, I think it is very useful. There's very little interaction that has to happen with the cluster. And I think, as a lot of us have experienced, you know, I can't tell how many people are running VS Code Server on the login nodes of Slurm clusters, but they're very unusable at times now. And so, yeah, not having to touch the cluster at all is, I think, I don't know, at least to me, that seemed like the way to go. And so, yeah, I don't know. If people have questions, they can ask now.
Yeah. My name is Fabrice. I work at IDT.
Okay.
And I would love to hear more about all of that. So is it open source? Are you working on it on your own? Like, what's when did you start working on this?
Yeah, I like cobbled this together in like the last couple of weeks. But it's like, like I said, the abstractions that XManager makes, they're, like I said, they're pretty meaningful. And so it was fairly easy to implement things. And so I don't really want to maintain this myself. It was mainly something I was building because I didn't like the way that job scheduling worked right now, and I know how things worked internally at Google. And now that it's open source, it's easier to do this externally. So, but yeah, I'd love to, if you want to hear more about it or how this can be made kind of easier. I think that doing something like this would greatly improve kind of the workflow at Mila. Yeah. So this is why I was saying that if you're running in a container, these Conda environments might be more useful. From my understanding, I'm not quite sure. So some of the packages that are compiled on like Compute Canada and Mila cluster, they have access to some like CPU specific like primitives and things like this. But from my understanding, some of the Conda packages, this is kind of the appeal of them as well, is that they'll have some of these optimizations baked into them. And from my experience, I mean, I guess it really depends on the workflow that you have and what you're running. There might be some of these optimizations that need to be made, but again, if it's that detrimental, it's a container, so you could compile things, you know, yourself or have a container that have some of these optimizations built into them. And that would also be something that would be useful if there was like a container registry for like for Mila, where there was just like pre-built containers that we know like are good on Compute Canada and Mila cluster and all of this stuff. So yeah.
Yeah, so one of my biggest pain points right now is like the speed of iteration of making small changes in code and fixing bugs. And so I like the idea of never touching the cluster when I'm sending a large job off. But I guess I'd like to know more about how this works when I'm like trying to change one line and make before I send my thing.
Yeah, for sure. So this is where I was like, I haven't done this work and I don't want to do this work myself, but this is where I like the idea of these like development containers. It seems that there are some people online that have tried to get these things to work with like Singularity, but I think like my hope in the future is like, you can click one button from like your editor and you'll be spun up in like a development container on a compute node. So you're not destroying the login server for everybody. And then you can actually kind of like test out your changes there. And then when you're ready to schedule, you know that it's going to run exactly the same.
So what would be involved with that is like you need to construct a container on the compute node.
Yeah, and hopefully, yeah, there should hopefully be some like good way to like automate this process. So like, I don't know, if you're in like VS Code or something like, so in a recent blog post that they had, they talked about this like VS Code like server. I know they already have this concept already, but from my understanding, they were kind of how they built this like the GitHub code spaces, this online VS Code editor. The server that actually kind of like runs this, they're working on releasing this. And so my hope was at some point that similar to how you access this, there's native support in VS Code to kind of connect to these development containers on a remote kind of server. And so hopefully in the future, you can like one click connect to like one of these development containers on Slurm or something, so you can test out like your GPU job or something. Yeah. Yeah. If you want to run what, sir? If you want to run like a simple test. Yeah, so correct me if I'm not answering the right question. I think the question was, how do I like, you know, I want to test out my code and not have to like spin up a job on the cluster. And you want to emulate the environment. Yeah. So this is where these like, as I was talking, these like development containers come into play here. So if you're on like Mac and you're running like Docker, there's like very easy support for this. Like I am on a Mac here as well, and I could this in VS Code, and you can do this, like I said, in other editors too now. You can kind of like open a development container on your local machine. And so you can, that's what I was saying, you can like develop against this development container on your local machine, knowing that that's what you're going to be deploying with. And so you know that it's, you know, if it runs for you locally and you're testing your changes locally, then it's going to run the same way on the cluster. And as I was responding to the question before, hopefully there's support one day for running these development containers on the cluster as well. So you can test against like GPUs or just like more powerful hardware than your local machine. Yeah, so I mean, speaking to like X Manager, that's the nice thing about it. It's completely agnostic to this. I could just as easily in my Python script that I scheduled use weights and biases, or like AIM, for example, that they were talking about earlier today. Or you could use like TensorBoard, for example. There's actually support for, in X Manager, they call them auxiliary units. These are things that might run alongside your jobs. And so an auxiliary unit might be like you're running TensorBoard, and it points to like a specific directory or something like that. So there is support for kind of doing these things in X Manager, but it makes no assumption on kind of what experiment logging or tracking you're doing. The only abstraction it makes is just like, I want to schedule something on a cluster. And yeah, I think I'm a little over time now, so I will. Oh, sure, yeah.
Have you talked with the experiment buddy people at all?
I'm not sure what that is now, so.
Oh, okay. So Manuel, and I'm not exactly sure who else, Manuel did that, then building this like piece of software that seems to something slightly complementary to yours. It's not containerization, but yeah, it's like zero interaction with the cluster once you drop onto the cluster, basically.
Yeah.
So it seems like that might just make sense.
Yeah, sure. Thanks for, I'll look it up.
Cool.
Thank you, guys.
So next we have Nikki, who will be talking about the Myriad control repository.
Awesome, thanks. Perfect, yeah. Test. Okay. Okay, can everyone hear me? Yeah, okay, cool. What's up, everyone? I'm Nikki. I'm going to talk about Myriad, which is some work I was doing primarily during my master's, but there's still a little bit of work ongoing right now. I guess we're now at the part of the event where we start talking about test beds and benchmarks. Yeah, this is the start, I guess, of the end of the workshop. So yeah, Myriad, a real-world testbed to bridge trajectory optimization and deep learning. And this was work in collaboration with Simon, who did a bunch of work in implementing different test environments, as well as Nitarshan, who sort of laid out some of the initial code structure, and all of this is advised by Pierre-Luc, who's my advisor. Okay. So what is the current state of affairs in deep reinforcement learning? We sort of have these standard algorithms. Okay, this is like the most interactive slide of the talk. So how about people shout out some of your favorite DeepRL algorithms? PPO. There must be some favorites, right? Who likes SAC? Woo! Rainbow, let's go. Any others? Any TRPO lovers? TD3, yeah, let's go. Okay, awesome. So yeah, all of these are like readily available, right? We have implementations for many of these in various places, including, for example, stable baselines, right? I guess has a lot of them. And then we like to test these algorithms or modifications to these algorithms in relatively standard and standardized, I guess, game and physics-based test beds, right? So we've got things like the arcade learning environment. We've got a bunch of stuff in Majoko. We interface with this using the GIM APIs. This is pretty much how things are done, right? Obviously, this has a lot of advantages. So we like to have standards against which we can compare algorithms effectively to see what's actually working better. In theory, having standard implementations might enable quicker iteration on top of this, or innovation where you can just modify a few things and see performance change. In practice, it's questionable whether that's always the case and whether the abstractions used are actually useful for making any changes. Yeah, I don't know. Does anybody have any other thoughts on how this is helpful for development, fostering a healthy RL research environment? There don't have to be, by the way. These are just, if anybody has thoughts, feel free to like interrupt. Okay. Yes, Fabrice.
I think we mixed up the problem we're trying to solve with the solution we want to give to that problem. And having a clear separation of concern between those two things is like the main way to solve this kind of thing. So that's why it works well.
Interesting. So you're saying a clear distinction between the problem and the solution to the problem is fundamental for like crisp understanding, basically. And this is where GIM is helpful.
For example.
Cool. Thanks. Yeah. Yeah, Florian. Yeah. Yeah, totally. Yeah, interesting. So if you're already a stable baselines expert, then it's great. But maybe a lot of layers of abstraction if you just want to do something. Yeah, totally. Cool. Well, maybe we're starting to get into the cons then, of which there might be a few, and we might hear more of in future presentations. So yeah, obviously, we talk about this all the time in supervised learning as well as RL, is overfitting ourselves to these specific problems is an open and unsolved concern. We've already mentioned a little bit how having everything be so standardized can limit the viability of very different approaches, or in some cases, even small changes that it's unclear how to do. So the GIM API, on the one hand, can be very helpful, but on the other hand, sort of restricts us to a very specific way of interacting with the environment. Yeah, at one point I was like trying to reset to a specific state, and it seems like you just can't do this without overriding like the reset method, which might be fine if you're willing to do that, but it would be nice just to have a bit more versatility, right? One sort of different angle, I would say, to talk about this from is that ultimately we want to apply our methods to the real world, but we're not really training them on real world problems. Then in conjunction with this, you have the whole sim to real issue. Yeah, perhaps we've already mentioned a few other cons, and so unless anybody has burning thoughts, I'll just move on. Yeah. Okay, awesome. So one response to this is to say, okay, we're going to make a new test bed that doesn't solve all of these problems, but it sort of circumvents some of them and provides a bit of a fresh perspective on the things that we can do with DeepRL. And so this is the Myriad repository, which it's available now on GitHub. You can go check it out. Please submit PRs. Would be great to have people who want to work on it. Yeah, it's a test bed for imitation and reinforcement learning. It's all written in JAX, almost all written in JAX. It uses a couple of non-differentiable libraries, but most of it is fully differentiable. It's got a bunch of real world environments described by systems of ODEs. User has direct access to this, right? So you can change the parameters of the environment. You can write new environments, no problem. You also have direct access to the cost functional, everything. It's fully continuous. So this is different from most RL settings that we see, right? This maintains a fair bit of the complexity of real world systems that we don't see. We'll mention quickly why that might be interesting. And then we also provide benchmark scores for a few different approaches to these problems. Notably missing right now is we don't actually have scores for deep RL algorithms. We have deep imitation learning algorithms, and we also have just straight up trajectory optimization on the true model, but we still haven't found the time and energy to actually get the deep RL working. And this, and Fabrice, I'll get to you in just a second, this sort of to preemptively answer maybe other questions about things that aren't yet done. I would say in terms of technical challenges, JAX lets us do just about everything we want to. It really has more just to do with, well, it's almost a solo project. And yeah, I've been focusing a bit on other things recently. So yeah, Fabrice.
So the question is, how easy would it be to just ignore the fact that it's differentiable and just apply a dummy kind of existing RL algorithm?
Super easy. Yeah, super easy. All you need to do is choose a discretization. Oh, I'll talk about this on the next slide, actually. I'll get back to this, okay? I'm just going to mention, yep, we submitted it to datasets and benchmarks. We'll see how it goes. But the paper has also been on archive since February. Yeah, I think, yeah, I get to you in 5 slides. Is that okay, Fabrice? Yeah. Okay. So again, what are we dealing with here? We've got environments which have dynamics and cost functions, trajectory optimizers, which given an objective and a constraint function, return an optimal control sequence. Nonlinear program solvers, which are used to solve the nonlinear program that comes from trajectory optimization. So this is sort of quite a different flavor from what we tend to see in RL, but actually solving a very similar problem and with the right tools. And I'm going to argue that Myriad provides a subset of those right tools can be used to great advantage in conjunction with RL. And then we also provide sort of dynamics learning module. So because it's continuous, we use neural DEs, but essentially this is just a world model learning for a model-based RL kind of flavor. And this lets us do a few things. So we can use trajectory optimization directly in our projects. So for example, if you have some problem that you're using RL for example, and you would like to use trajectory optimization for it, you can go right ahead and use the tools that are built into Myriad. It also serves as a benchmark against trajectory optimization for deep RL, and also allows interoperability between RL techniques and neural network-based techniques in general, and trajectory optimization, which historically we really haven't seen much of. So, you know, we do have these maybe OR, operations researchy, trajectory optimization, and maybe some robotics frameworks which support trajectory optimization, but then they don't also support deep learning within that same framework. So this is the gap we're trying to bridge. Yeah, just another quick answering some natural questions that come up. Okay, obviously we want it to be real world, but actually we want it to be real world, right? Continuous time, not only does it make it harder and more interesting, but it's also more realistic in some ways. So we can deal now with irregularly spaced data, which is a struggle in if you have a fixed discretization. And you can also take advantage of integrating both at sort of variable steps to speed up your computation, but also different, again, dealing with adaptive step sizes essentially to fit speed, but also precision requirements. And this is something that's, you know, if your integration method, whether it's Euler or RK4 or something else, if it's built into your simulator, you don't have any control over these things. So we're saying, okay, just give the control back to the user. You get to choose what integration method you use. You can even use variable step. You can differentiate through the variable step integration, whatever. And then, yeah, just a note on trajectory optimization. Although we don't talk about it in RL, it is sort of an industry standard. So in robotics, I guess, it's fairly commonly used. for various things, but also in aerospace, it's ubiquitous, and it's often also used to solve sort of these heavy industry problems like chemical engineering. Very happily, it allows us to, most of these algorithms allow us to specify constraints on the state trajectory, which is something we struggle with sometimes in RL, I guess, which is a nice, important component for safety. And yeah, it's rarely seen, as I said, in deep learning. This is for a couple of reasons, usually with the simulators, I guess, or trajectory optimization frameworks are not differentiable, and also they're optimized for CPU computation. And we sort of get rid of both of those problems by writing everything in JAX and by writing everything in JAX. Yeah, pretty much. We'll talk a little bit more about that later. Yeah, so Fabrice, your question will be answered on the next slide. So yeah, 18 or so continuous time real world environments. Most of them are fairly straightforward to solve with pure trajectory optimization. Of course, compared with the RL problem, this is sort of strictly an easier problem because we do have access to the true dynamics. But you know, many of them can even be solved if you just sort of very naively do some rollouts, fit a model to the dynamics that you see. This can either be you're doing parameter sysid parameter identification, or straight up black box neural network based dynamics estimation. And maybe if you use some model predictive control here, then actually it's not too hard, perhaps. But interestingly, so some people in my group, in Pierre-Luc's group, have been using this, I think, already for a little bit. And it seems as though some of these problems might be not so easy with RL, which again points to it being an interesting direction to test RL in. So yeah, this is just an example of one of the problems where you're trying to control a prey population through use of a pesticide here. And yeah, the output essentially of the trajectory optimization algorithm is just a control signal, a continuous control signal. But I want to focus on this finite horizon control system, which is sort of the equivalent of an MDP when we're talking about trajectory optimization. So all of us here probably are familiar with this sort of Satonian diagram, right? And this sort of, you're in different states and you take actions and you receive rewards based on that. And yeah, I'm arguing here that a finite horizon control system is really not all that different. All you have to do to get an MDP is fix a discretization and choose an integration method. And essentially you're back in an MDP setting. But it allows a bit more flexibility than this. So you can not fix a discretization, I guess, and treat it as an SMDP, or you can leave it in its fully general form and just integrate both the dynamics and the cost functionals over time as you take actions. Yeah, so it's just trying to minimize the overall cost. That's just like RL. Maybe there's some final cost subject to these dynamics starting from some start state. Did I answer your question, Fabrice? I feel like I said I was going to, and then I actually think I forgot whether I have or not. I think I thought this slide was going to. Yeah? Does it answer? Yeah? Okay. And yeah, just going a little bit quickly here. Here are some of the, I guess actually this is all 18 of the environments. So you can see practically all of them are very real world inspired. In fact, many of them come from this book by Lenhart and Workman. Optimal control applied to biological models. This was Simon's big contribution. He implemented the majority of these. So yeah, all of these are very real world relevant problems, I guess. And then we also have some classical control problems sprinkled in there, inspired by the OpenAI classical control, the GYM classical control problems, like, I don't know, pendulum, mountain car, cartwheel swing up, whatnot. All of these, by the way, very easy to solve with trajectory optimization. Yeah, the framework is also ready to support variable time horizons, but for right now we have fixed episode length. Yeah, so just to give a bit of a flavor for how you can use this, specifying a new environment is actually pretty simple. You just need to match the template. So you give an initial state, whether or not there's a required final state, time horizon, bounds that you require over the states and over the controls, and whether there's a terminal cost or not. It also supports discrete environments, but we're not too interested in that. Then for the dynamics function, it just takes the state and actions. Ignore the V, that's the duals, I guess. That's if you want to use sort of implicit solving methods. You don't need to provide that. And yeah, time-dependent dynamics is also optional and not recommended. And so here, yeah, we have some dynamics that are linear and control and quadratic in X, I guess. But you can have whichever dynamics you want, and you can also have whichever cost functional you want. And this gives us a trajectory optimization problem. So given that we have this model, we can do trajectory optimization directly. If we don't have the model, we can learn one, and we'll see very briefly some examples of that. And we have sort of a nice collection of different algorithms implemented in Myriad. So direct collocation, single and multiple shooting, as well as an indirect method, which is the one that is presented by Lenhart in this book. By the way, if you're at all interested in trajectory optimization or just using optimal control techniques for like RL-like settings, I'd recommend for collocation, this paper by Matthew Kelly is really nice. Goes through sort of a full worked example. For shooting methods, which are perhaps the most commonly used and referenced, this Practical Methods book by Betts is a really great resource. Yeah, so let's just work through an example very quickly. I guess probably everyone's a bit tired, so maybe we won't focus on it for too long. So here's a rewriting of our minimization problem that we want to solve. We discretize it. For simplicity, this is a fixed step discretization, but you can imagine it being a variable step discretization. And yeah, here we actually augment the dynamics with the cost so that we're integrating the cost over time as we integrate the dynamics. That's sort of a nice computational trick that makes things work well with the continuous dynamics, I guess. Yeah, single shooting basically says guess the controls, miss the target, and then adjust by the gradient of the miss. So perhaps fittingly, yeah, you see we're trying to get the little Starship rocket to hit the drone ship. You can also add inequality constraints on the controls. So these are, I guess, bounds. I guess we already have this, right, in RL. But what we don't have is the ability to really parallelize over a single trajectory like this. And this is what we have with multiple shooting. And in the limit, you can parallelize over each individual time step. That's what ends up being a collocation. And you can see in this case, if we do this kind of thing, you can actually add bounds over the state trajectory as well. So for each a shooting interval, they're called. Here we have 5 shooting intervals, and you can see as we increase the number of iterations of the solve, we get closer and closer to finding a viable set of controls that leads us to a viable trajectory. For each interval, we can impose one constraint on where the state has to be. And so if we make those intervals really small, you can actually fully constrain, your, so if we let k equals 1, basically, you can fully constrain your state trajectory to be between within some, safe region, for example, if you'd like. Yeah. So how does this fit into the deep learning that we were talking about doing earlier, right? How does this work on GPUs? So traditionally, the way you would solve these nonlinear programs, like this type of nonlinear program with an objective and equality constraints and inequality constraints, is by using, is by using something like SQP. Probably you've heard about this if you've taken some, I guess, nonlinear programming class, or maybe Pierre-Luc's class. I think he talks about it a lot. You also have interior point methods like IPOpt. So this is from the operations research community. You also have, trust region methods. The issue is, as I mentioned earlier, all of these historically are optimized to run on CPU, and they take advantage essentially of the sparsity of the Jacobians in order to get computational efficiency. But in this case, at least at this point in time, we don't really care much about sparsity on CPU. We really just want to take full advantage of the GPU with as dense operations as necessary. And this is where we can actually use some very simple but effective methods. So I guess everyone's heard of gradient descent, akin to what is perhaps used in the simplest GAN training. But there's also extra gradients, which some people at Mila, I guess, have been working on, also in the context of GANs, which takes a look ahead step. And this eliminates a lot of the instability that we see with gradient descent, and turns out to be powerful enough to actually solve a significant chunk of the nonlinear programs that we want to solve, which is somewhat striking. I will mention that there really is like a lot of work to be done here in using sort of quasi higher order, but still first order methods for these solves. If anyone's interested, I would love to hear about it. So far, I've had difficulty making them fast, despite the fact that we're using JAX. Seems there's just a lot of stuff going on, and it's hard to compile it all effectively. Yeah, as I mentioned before, here's just the look ahead step in extra gradient. But the cool takeaway here, right, is that these things that historically only ran on CPU and that we couldn't really think about using in the context of deep learning, all of a sudden now with JAX and with these first order methods, we can start incorporating them into our reinforcement learning algorithms. Yeah, as I mentioned before, okay, the RL problem in general doesn't give you the model, of course, right? That's sort of half the problem. Well, that's fine. We can just learn one. So we can learn neural ODE world models to predict dynamics. You still run into the same challenges as you do in model-based RL, right? So exploration remains an issue. How your model is going to generalize, I guess, is another side of that same issue. But you can see that in these environments, we seem to do a pretty good job, at least in most cases, of matching the dynamics with some fairly naive exploration approaches. So here, yeah, these vectors represent the dynamics. This is very nice. Here we have like almost perfect prediction for the rollout. And then in some environments, we just don't. So this is similar problems to model-based RL. Yeah. But not having a model is not the problem. Yeah. And just finally, before essentially summarizing and concluding and taking questions, I'd like to give an example of how the fact that everything runs on JAX and almost everything is differentiable really lets us leverage trajectory optimization in the context of deep imitation and deep reinforcement learning, and might be interesting for all of you if you're interested in sort of developing novel algorithms that use aspects from control theory. So this is the sort of controls and resulting state trajectory that is learned with an end-to-end trained imitation learning model that does planning over an implicit dynamics module. So actually, I guess some of us were talking during the break in that part of the room that all of a sudden, if you have differentiability, now you can implicitly learn a model just based on, well, in the case of RL, the reward signal, in the case of imitation learning, the supervised loss. So yeah, this is ongoing work to see if this works well in the context of reinforcement learning. But really, the important message here is that there's a lot of untapped potential in using optimal control techniques in conjunction with RL, if you have a testbed that actually supports it. Yeah, so we have benchmark scores for a bunch of different approaches for solving these problems. Still, as I mentioned before, have yet to get our different favorite deep RL algorithms that we mentioned at the start benchmarked on them, but there's no conceptual challenge here. It's just a matter of doing it. Yeah, so to conclude, this is Myriad, which is you can find on GitHub. Testbed and benchmark for imitation and reinforcement learning with real world applications. But it's also a set of tools for trajectory optimization to use directly in your problems, for example, in robotics problems, as well as sort of a testbed on which to build new algorithms that merge deep RL and optimal control-based methods. Yeah, so we want more versatility and diversity in our testbeds for a positive real-world impact. Let's do this together. Hopefully Myriad can help. Okay, thank you, everyone. And I guess I'll just vacate the podium if there aren't questions because I'm a couple minutes. Oh, sorry, Brendan. Yeah.
So it seems like one use this to leverage GPU, and so it's useful in high dimensional settings. And I showed some examples there where you can think analytically
Yeah, sure. You're talking right here, right? Yeah. This is like a very low dimensional example, of course. Yeah.
Yeah, so I think this is, compares with other solvers, and you can compute like path integrals or certain integrals in higher dimensions.
So okay, so it seems like there are sort of two questions bundled into one, if I'm not mistaken, right? The first one is how well does this work in higher dimensions, essentially, and the second one has to do with integrating flows. Is that right? Yeah. So the first one, I would say, probably the highest dimension that we've used so far is not higher than, I guess. I think we can go up to like several hundred probably and still have these be effective. Yeah, I think once you get past 1,000, it might break down. But I think I can say with some confidence, certainly above 100, no problem. Yeah, probably comfortably into the hundreds. But yeah, I think there's still a lot of work to be done in understanding the actual like loss landscape, or well, it's not really a loss landscape, I guess, if you're like trying to find a fixed point. But well, I guess it's the Lagrangian landscape, let's say. And work specifically that remains to be done is understanding how we can exploit the fact that like half of these decision variables are dual variables, right? And so don't change, and basically the Lagrangian is just linear with respect to them. So there's a lot of structure that we're not exploiting, both in terms of the Lagrangian structure and in terms of the fact that the nonlinear program that we're trying to solve comes from trajectory optimization techniques. And so, your dimensions that you're considering are correlated in some sense, because one control comes after the other in time, and it's going to depend on what happened previously. And in particular, the earlier controls are going to be much more impactful. So there's a lot of work to be done there. As far as integrating the flows question is concerned, I'm not sure I fully understand it. But certainly we can use these integration techniques for other things. So for example, one thing that comes to mind is, you say, gradient descent, actually you can treat that as a control problem, right? It's just an Euler discretization of a gradient flow. Well, yeah, of course we can use we can use variable step integration and stuff like this, but we can even go further and treat it as a control problem. So this 100% works, yeah. Yeah. The spatial coordinates are all continuous. Yeah, it's just in time that we eventually discretize. Yeah, for the integration. Yeah. Yeah, thank you. Thanks, everyone. I'm okay, thank you.
Okay, so next we have Darshan to talk about RL Hive.
One sec. All right. Hello, everyone. My name is Darshan, and yeah, I'm going to be talking about RL Hive, which is a RL research framework that my lab has been developing for the last like year and a half or so.
So I guess before I get started, I just want to acknowledge the blood, sweat, and tears of all my fellow collaborators, some of whom are in this room. So there's Hadi Nakui, Ali Rohimi Kalarudi, Sai Krishna, Shreyash Podar, Kshitij Gupta, Zutong Zhao, Soma Karthik, Mariam Hashimzada, and my advisor, Sarat Chandra. So all of you are probably thinking like, another RL framework, like, why do we need another one? There's so many, like, stable baselines has been talked about as such a viable alternative up until now, right? So yeah, why do we need another RL framework? So yeah, I guess in this presentation, I'll talk about kind of the things that we tried to keep in mind while developing this framework, and why I think you guys should try using Hive, other than to make me happy. Yeah, so why should you use this? So first of all, when sort of just doing the setup for Hive, we tried to make it so that there's like very few sort of dependencies other than like the core ones. And like, if you want to add more stuff, you can like install them as extras and stuff like that. But like, it's very easy to just like install and just get started with. There's like horror stories from my lab where it's like, some of my lab mates were trying to install some random framework and it took them like weeks or months. And we want to try to, avoid that and just make using Hive like as easy as possible. Another thing is when designing Hive, we try to make it make like the sort of API very sort of high level and very simple. So that gives us a few things. So one, so like, everyone talks about like, modularity and how like, oh, all their code is very modular and how like modularity is a good thing. The problem with modularity is like, sometimes you can be too modular, and that like makes code, that sometimes makes code like a lot harder to sort of read and use and get into. Like there's a lot of libraries out there where they have sort of a bunch of different layers of abstractions. And once you get into them and once you sort of realize how to use them, it's great. And you can, like make one small change and try out a bunch of new things. The problem is like, that's a very steep learning curve and it takes a really long time to do that. And so we try to, like you want to have like small pieces, but you also don't want to have too many pieces. And so like there's a balance with modularity that needs to be struck, which we think, we try to do a good job of. So like, like as an example, like all our agent, our sort of agent classes, like the main methods you just have to update to write are like act and update, which, it's very sort of like high level. You can do whatever you want. Like it's just, there's you have to say how the agent acts and how it updates itself. The environment is like the basic, step, reset, render, stuff like that. But point is like, we try to give the user a lot of freedom. And so this also means that, generally the code base is easy to read and modify. So, you can look at like a couple of files and generally like, that's all you need to read to like sort of figure out what's going on. You don't have to like wade through like several different layers of abstractions to find like the specific method that's doing like one thing. It's all mostly in like a couple files. And the other thing that does, which I think is a very important part of research code, is that it better communicates the ideas that you're trying to talk about. Like research code isn't like, okay, in my opinion, research code isn't just about like getting your experiment to run. It's also about like, communicating the ideas in your research ideas. And so if somebody has to go through a bunch of different, like if it takes a really long time to understand what's happening with your code, then your idea is less likely to be used. And yeah, so kind of jumping onto the point that Jacob brought up in his presentation about like, having more sort of template-like codes, template-like sort of files. That's kind of what we tried to do too. So it's like, we're not breaking down the sort of all the different sort of, utilities within an agent that much. It's just, the DQN is like one sort of file, And there's a couple of small utility functions that we use, but mostly it's all in one file. So it's like, if you want to change something, you just like kind of copy it into your code, and then you just change a couple lines. And yeah, so it's easier to sort of, it's because it's all in one place, it's easier to modify. And yeah, I guess kind of shamelessly also jumping onto what Nikki was saying, it hopefully doesn't overfit you into a usage pattern, like, kind of, for example, like stable baselines, like for a class project, we were trying to write a hierarchical agent, and to make it work, we had to do all this, we had to jump through all these hoops of like writing environment wrappers and all that sort of stuff to get like a hierarchical agent working, which, ideally you want the way you think about the code to be as natural as possible. So another, reason why you should use this is that we have, a pretty good coverage of the most popular components in the RL literature. So what do we have? On the agents, we have DQN and Rainbow with like sort of every, possible combination of, variant. You can turn them all on and off independently. We have DD, PG, and TD3. We have PPO, and we have recurrent DQN and recurrent Rainbow. On the environment side, we provide support for pretty much all GEM environments. So as long as you can register your environment with GEM, you can just directly use it with Hive. We have Minigrid, Minotaur, and Mojoko, just like pretty simple setup, just natively supported. And on sort of the multi-agent environments, we have support for things like Petting Zoo, Hanabi, and Marl Grid. For replays, we have a memory efficient circular replay buffer. So like, there's some implementations out there which sort of double store things like observations, things like that. We try to make it so that the replay that the replay is as memory efficient as possible, so you can potentially make the capacity larger, or like you don't have to you're not using too much memory. And on top of that, we have a prioritized replay, a recurrent replay, an on policy replay, which pretty much just replays your most recent transitions. Yeah. And then for the runners, we have a single agent runner and a multi-agent runner. Yeah, both those are just kind of natively supported with Hive, and we try to make both of them like sort of equally first-class citizens. And yeah, and for the utilities, so for logging, we have we have 1DB logging and file logging. We have support for saving and resuming experiments. We have sort of easy integration with like matplotlib visualization with our sort of with the file logging. Like pretty much you just provide the directory where all like the runs have been logged, and you can just generate matplotlib graphs. We have reliable integration. Oh, also, these are all going to be released in like the Hive 2.0, which is going to be in 1 month. So some of these are like currently in development, but will be there in a month. We have reliable metrics. We have parallel environments. So stuff like, like vectorized environments and Unpool. Parallel step environments. So this is for like multi-agent environments where you want all the agents to take a step at once rather than one at a time. We are planning on having Orion integration. So, it's easier to just run your hyperparameter search. We make it super easy to just override parameters from the command line. I'll give an example of that later on. And also we have a magic registry that kind of recursively builds all your objects for you and makes everything super nice. And I'll give examples of that as well. Nikki, you have a question?
Yeah, I was just a really small one. What's the distinction between Hanabi and Marlgrid from the others?
Well, okay, so Petting Zoo, Hanabi, and Marlgrid, they're all multi-agent environments.
Oh, okay.
The other ones, well, Jim can also be, I guess, multi-agent, but like in general, I guess. Actually, I don't know if Jim technically supports multi-agent or not. But yeah, the main thing is single agent versus multi-agent. Yep. And also more to come. So these are things that, so these are all things that we're planning on having within essentially like the Hive 2.0 or 2.1 release that's going to happen in like a month or so. These are the sort of things that we're planning on doing in a slightly longer out, like in a few months. So one thing is we're planning on like supporting JAX and making it so that you can sort of you like essentially put in a PyTorch agent or a JAX agent into the same pipeline, and hopefully, you know, it should just work and you should be able to run it. A model-based RL, model-based RL agents like Dreamer, SAC, and also recurrent versions of all the agents that I talked about. Hindsight experience replay, an RL debugger. So, you know, one big problem in RL is that it's very difficult to find out, you know, why stuff is going wrong, if it's going wrong. And so we're working with some students in the Poly sort of software engineering department, and we're trying to, you know, create a way for you to like it would like log sort of common metrics that are sort of it would sort of like log and track metrics that are useful for RL debugging and like give you warnings if like stuff seems wrong, and also just give you a way to add your own, hopefully. And as a part of this, we're also probably going to add like, you know, probe environments and probe agents, things like that, just tools to make RL debugging easier. Also for this, if any of you have like sort of, you know, things that are on your, like if you have a checklist of like, oh, this is what I try when like stuff goes wrong, like please feel free to send that to me, because this is still a, you know, an early effort and we're trying to figure out what people do. And yeah, and also adding a lifelong RL runner and an offline runner. So why else should you use? So one, we have benchmark implementations of, you know, all the sort of common agents that I talked about. So for example, like, you know, here it's this is TD3 and DDPG on Mujoko, and on the right is like DQN and Rainbow on like Atari. And we've benchmarked these against implementations from like Dopamine and CleanRL. So, you know, you can trust us. You know, this is research. And in research, you often have to try new things. And so we've tried to make it easy to add sort of custom components and types. So like, you know, if there's a new thing that you want to do and it's not really supported through Hive, you know, one thing that is nice is that you want to be able to like just easily sort of create and configure that object. So we make it very easy to just like set it up with the Hive registry and like be able to automatically configure those things. And the last reason you should use it is because it's homegrown. This means that one, you get instant support, and two, like we're developing these on this on like, you know, the same clusters that you'll probably be using, and so it's more likely that we will have thought of issues you would run into, or be able to help you out if you run into any issues. So I just want to go through kind of like a basic agent API and kind of like give you a taste of kind of like what it would look like. So, you know, for an agent, what you need to implement is, you know, like an act function that would say take in an observation, and an update function that would take in, you know, like an update info dictionary. Very simple, very sort of high level. Like you can implement, your agent can do whatever it wants with these things. It's just, these are the only things that we require. Now say you have your agent and say you called it a DQN agent. Now the next step is to register it with our registry. And so here, like, you know, you just register you register it under like this name DQN agent. This is like the class, and then this is like the sort of type. And then when you sort of use the registry, you could say like registry dot, you know, get agent, and you just pass it the config, and you, instead of returning the actual agent, what it returns is a function that will create the agent. And the reason for this is because it turns out that lazy sort of creation of objects is much nicer for a lot of things. You know, like researchers are lazy, we want to do it as late as possible. So like, you know, something that it can enable you to do is like configure all the sort of configure like all the sort of parameters that you want from the command line that like won't change, but then say there are things that you won't get until sort of runtime, you can pass them at sort of runtime instead of having to instead of having to sort of configure them at code writing time. So for example, here, like an observation space and an action space that's dependent on your environment. Ideally, you want the framework to just get it from the environment. Like you don't want to have to write what the observation space and action space will be. So by using this sort of like lazy creation, you can just give that responsibility over to when it's a lot easier for you to do. This is an example of like kind of this is a modified sort of clipping of the code, but like here you have your things like your observation space, your action space, your sort of function approximator, and various other things. So all of these are sort of partial functions. They're not actually like the full thing yet, but they're like parts of them have been configured from the config, and then when you create them, like for example here, like this optimizer function, like here you have like your QNet parameters, right? This like you wouldn't have until runtime. So now you can just but like there might be sort of other parts of the optimization function or optimizer function that you wanted to configure from the from your config, like Atom, like you might want to set the learning rate or something. So now you're able to sort of have the best of both worlds. And like same with the replay buffer, things like the observation space or the observation shape and like data type, you get that at runtime. You don't get that at sort of code writing time. So here's a kind of a basic config that you could use for something like this, right? And so here here we're sort of defining the sort of MLP that's going to be the function approximator, the optimizer, the type of loss, and then like the replay buffer. And here we can also provide, we can sort of recursively also like provide parameters. So it's like this replay buffer will have a capacity of 1,000. Now, that's all great, but like what if like, you want to try out a bunch of different hyperparameters for this, right? So you can also modify the base config from the command line by just sort of doing something like this, where you kind of just go down the you just go down the sort of parameter names and modify whatever variable. And this doesn't require any extra work. Like as long as it's a sort of the type is a registrable like Hive type, Hive just automatically does this for you. Like it automatically allows you to do this modification, and it automatically just recursively creates all of these sort of complex objects as partial functions. Yeah, so now I'm gonna just talk about a couple of case studies. So one thing, like what if you want to add like say custom types? For example, while trying to recreate some DQN results, we realized that for some environments or for some types of agents, you need to initialize the network with like different initialization functions, and we didn't particularly want to write a whole sort of thing that would like we want to just like reuse what Torch already had, right? And so here we just like registered the initialization function. Like here we created the type. All this does is it just creates it just sort of defines a type name. This is supposed to be get initialization function, sorry. But yeah, so here this just you just take the you just provide dictionary sort of mapping of the sort of name to the function that creates whatever you're trying to do. Yeah, and so you can do this for whatever you want. Like it can be whatever, and you can just directly then configure them using like your config files or from the command line or whatever. Another sort of case study is the hierarchical. So we like in my work, I was trying to create like a hierarchical sort of off or like an off policy agent essentially. And, I tried to do this in stable baselines and it was a nightmare. And so, but in Hive, it's, pretty easy because all you have to do is define this sort of signature. Oh, the registry uses like the type signatures to sort of automatically figure out like what type of object it should create. So here, like with this type signature, like all I have to do is this, and then all of these are and then I get like the function for creating the forward agent, behavior agent, and it's just a lot more sort of natural. I can pass, I can by passing off the responsibility of actually creating the agent to when I have all the information. Like the configuration is a lot easier. So for example, here, like this is the configuration that I used. Like I have my top level agent, and then I have my behavior agent, and this is just like the TD3 like agent that's in Hive, and I like provide all the sort of configuration that's needed, and yeah, it allows you to more sort of naturally think about and create your agents or objects or whatever. And yeah, like when you're doing the act, like the act and update functions here are also like very simple, right? It's like if you're training, you want the behavior agent to act. If you're not, you want the forward agent to act. The update is some combination. But yeah, point is like it like but you can sort of create nice abstractions and things as well. Yeah, that's all I have. I'm ready for questions, I guess. Cool.
I have a question.
Yes.
Very specific one. How easy is it to reset to a very specific state midway through training?
I mean, it depends, right? Like it depends on like whatever your sort of like we use like gym, like our environments and stuff are just like wrappers around sort of existing environments and things. So yeah, like if it's easy to do in like whatever other thing you're using, it's easy to do here, but it's not.
Okay, I see. So
Yeah.
the responsibility is still in Jim's hands in some sense if I'm using a
Yeah.
gym environment.
Yeah. So the idea is pretty much just like we want to provide a loose framework because like we don't want to just like nail you down to a specific thing because different research projects have different requirements, and so
yeah, makes sense. Thank you.
Yep. Cool. Anyway, use Hive. That's ending statement. Oh, I did not notice. We currently don't. The plan is to like once we get like V2 out, like the next version will have support for offline RL. For config right now we don't use Hydra. We use like our own sort of system, but I think the plan isn't. We're not gonna use Hydra, but we might use like there's like a underlying config system that Hydra uses, which is like Omega Conf. So we might like use that. There's like a couple things with Hydra that are kind of annoying. So yeah.
All right, I guess that's sort of like the end of the overall workshop. It's been great getting to hear about like the number of different new technologies that people are using in order to make, different versions of getting, research to run faster, research to run easier, or actually do some research you couldn't be done before, which is especially the last two presentations and some other stuff. I guess I did, as being a professory kind of person, I put together a document that I shared online on the Slack channel. So if you want to dump a few of your ideas or some of the stuff we talked about today, it could also help as a thing that we can like give to the IDT department and build on, so we know what priorities we have. So if you've got 3 minutes, you can go put a few thoughts on that as well. Otherwise, yeah, thank you everyone for coming today. I'll post the recorded video for stuff too, so people can share that for later who couldn't make it. But otherwise, have a great day. Thank you very much. And thank you again to all the speakers. Very much appreciated.